All right, welcome everyone to our chemistry IGCSE revision session. I am your teacher, Miss Fatma. I have been teaching both IGCSE as well as A levels for about 10 years now. Really excited to be teaching you all. We have kept this session just for you guys specifically to help you guys out because I know we're very close to the exams right now. There's a lot of syllabus to cover, especially in sciences, and it is you really need help at this point, especially with the past papers practice, right? So we have kept this a revision session for you guys, and for you guys specifically, just to help you guys out as much as we can, so close to the exams. So our Academy X, has about over 10 to 15 years of experience when it comes to teaching both IGCSE, A levels, as well as IB. We have been conducting classes for that as well. And specifically, so we are starting with our next batches really soon. We're taking students up in August for the next May June exam. And please go ahead and take a screenshot of this. It has all the information. It has our website mentioned on it. It has the number mentioned on it, the WhatsApp number, the website. Please go ahead and take a screenshot of it. We have a QR code as well that you can scan to access our website. And go ahead and take a screenshot of this. So if there are any queries, any admission queries that you guys have, please don't hesitate to contact at all. Also, please remember to sign up at the resource center on our website. Okay, you will be given access to the you will be given access to obviously the class today on the website after we're done with the class. So please go ahead and take a screenshot of this. Now we're going to go ahead and start off with our revision session. All right. So this is the schedule that we are going to be going about today. We're going to okay, so we're going to cover those topics that I think are really important for your exams. Obviously, we have a really small amount of time right now. We just have a few hours, which is not enough to cover the whole syllabus. So what I have done is that I have taken up all the important topics or topics that I feel like are crucial for you guys to understand while going through your exam questions, and we will be going over those specifically. Again, I can't go over the entire syllabus with you guys because we are really short on time, but I am going to go over as many important topics as I can to make this as easy for you as possible. So this is how we have divided our session. We're going to start with organic chemistry, take a look at our topic of acids and bases, and then, of course, periodic table, metals, electrolysis, mole calculations, really important, and then rate of reactions, dynamic equilibrium, and chemical energetics. Other topics like the air, water, environment, Haber process, contact process, I obviously could not include them on such a small time. I wish you guys had been there with me from the start. I would have absolutely loved to, go over those topics with you. And we are going to go ahead and finish off with a question answer session where you guys can give me any queries, any questions that you might have, and we will go ahead and we will go over them. Meanwhile, if you guys have any questions during the lecture, during the while we're covering the topic, if you guys have any queries, if there's anything that's not making sense, go ahead and do drop your question in the chat, and I'll get to it as soon as I can. All right. So let's go ahead and start off with the first major topic that you have, right? You guys know that in your MCQ paper, as well as your paper 4, one of the organic chemistry is one of the major questions that's there every single time. Like, it's a guarantee you're going to have questions on organic chemistry. So that's a really important thing for us to tackle. But when it comes to organic chemistry, there are a few parts of it that I feel like at least are not taught that well when you especially when in school. And one of them is obviously how you're going to go about naming organic compounds, right? It just doesn't make sense at times. I mean, so the thing is that there are certain rules, right? If you follow these rules, you'll find out that it's really easy whenever you are giving a name to an organic compound. And we will practice some questions on this as well. So you will see exactly how to go about it, right? First of all, let's go ahead and tackle the rules that you guys need to know, right? Now, I have simplified the rules. The rules that is we have a naming system. It's known as the IUPAC naming system, has a bit of elaborate rules. I have simplified them so they're easier for you to understand. Now, going over the rules, right? I will first list down the rules for you, and then I will explain to you how to use these rules to actually go about answering your questions. Now, the four major rules that I will really help you out is first of all, you have to identify the parent chain. What is the parent chain? When we talk about the parent chain is the longest carbon atom chain in your organic compound, right? So what does that mean? That means that let's go ahead and say I have a structure that is something like this. I asked you guys, can you please go ahead and name the compound? What's the first rule that you guys are going to tackle? You guys are going to try to figure out what is the longest carbon atom chain, because that is going to tell you exactly how to name the compound. I have 4 carbon atoms, right? I think you can all see we have got 4 carbon atoms. At this point, I think you are all aware that when we have 4 carbon atoms, the butene, butanol. Now, but this will not be named but. Why? The reason I will not be naming it but is because if we try to connect the carbon atoms, if I try to connect these carbon atoms to make one continuous chain, there can be no breaks. I cannot make a chain of more than 3 carbon atoms, right? That's it. It doesn't matter how I try to draw this chain. If I make a continuous chain, the maximum chain I can make only has 3 carbon atoms, meaning that when I'm naming a compound, I'm not going to be using but, I'm going to be using prop, right? I'm going to be using the suffix for 3 carbon atoms, not 4. So even though there are 4 carbon atoms in the compound, it's not going to be named based on that. It's going to be named based on the longest longest continuous carbon atom chain that we can make. And we're going to practice this in just a little bit. So this will become a bit more clearer. This is rule number 1. Then the second rule you need to take a look at is you need to identify what functional group is present in your compound, right? Now, when identifying functional groups, here in front of you is a table of all the functional groups that you can find in organic chemistry. There's some of them that you have not done in your syllabus, and that is fine and well. There's some of them, though, that would be quite familiar. For example, like we have an alkanes, right? Alkanes are basically those compounds that have single covalent bonds between the carbon atoms, right? They are simply hydrocarbons and they've got single covalent bonds. So we can have alkanes, in which case the suffix is "ane". The suffix is "ane", meaning that if I were to put this compound in front of you guys and I asked you to name it, so you would name it propane, right? That's not the full name, but that's part of the name. Propane, because it's an alkane, you identify the functional group, and prop, you identify the longest carbon chain. So propane. If we had an OH group, obviously that would have been alcohol, and in that case, it would have been a OL suffix, right? It would have been propanol. Similarly, if we have an alkene, propene. Alkynes are something that you guys have not covered, so you guys can go ahead and forget about it. Similarly, aldehydes and amines and ethers are also not a part of your syllabus, so you can forget about these for now as well. But esters, right? For esters, we can go ahead and we use the suffix of ate, right? So, for example, methyl proponate, right? If I'm naming this, I would name this proponate if it was an ester. It's not an ester, but that's what I would name it. One functional group that is not mentioned in my table that I wondered if any of you noticed is your carboxylic acids, right? Carboxylic acid would have a COOH group. And in this case, the suffix would be obviously oic acid. So if this was a carboxylic acid, it would be a propanoic acid. So step number 1, identify the longest continuous carbon atom chain. Step number 2, identify the functional group. Step number 3, identify any side groups that might be present. Any side groups. Do you have, for example, a methyl group present on the site, right? Rani, don't worry. We are going to be going over all of these in detail. Right now, we're just discussing how to name it. So we will discuss about how an ester is formed, how an ester is formed, what is the functional group, what is the reaction, and then obviously I'll explain to you exactly all the details about it, right? So we will follow that up later on. Right now, we're just getting the basics of naming it down. Okay. Then we are going to identify what the side group can possibly be. So in our particular case, you can see that we have a CH3 group, right? A CH3 group. So this obviously has one carbon atom. If the side group has one carbon atom, we will say methyl. One carbon atom is meth. So this is methyl. Your side chain could be maybe chlorine. It could be bromine, right? It could be C2H5. C2H5 has two carbon atoms, so ethyl, right? So you will identify what is the side chain that is present. And then the last thing you have to do is figuring out the numbering of your carbon atoms. Now, I will explain to you exactly what I mean by this by naming the structure that I have drawn for you guys. Now, naming the structure that I have, let's go ahead and name the structure. So if I name the structure, we will start by first identifying the longest continuous chain. We all discussed that that's going to be prop, right? Then we will identify the functional group. This is clearly an alkane. So I will write down propane. Right? Now, I have to identify any side chains that might be present. I do have a side chain. I have a CH3 group, right? This has got one carbon atom. Since it has one carbon atom, we will say methyl. We will say methyl. And finally, we have to figure out the numbering of this. How do we go ahead and figure out the numbering? Now, this structure I have drawn is quite easy. It doesn't matter whether I start counting from the left side or the right side, I get the same number. What do I mean by that? I mean that if I count from the left side, 1, 2, 3. Or I decide to count from the right side, 1, 2, 3. Regardless of which side I decide to count from, the methyl group is on carbon atom number 2. So this was an easy structure for us to number. But what if I take a structure quite similar, make it slightly complicated? What if I go ahead and give you something like this? Now, this is a very similar structure to the one we just discussed. But as you can see, in this particular case, the longest carbon atom chain that we have, the longest carbon atom chain that we have includes 4 carbon atoms, not 3. It has 4 carbon atoms. It doesn't matter how you decide to draw the chain. You decide to draw it like this, it's still going to be 4 carbon atoms, right? 4 carbon atoms. The longest chain has to be the longest. The longest continuous chain that you can make will be the will tell you the number of carbon atoms. So 4 carbon atoms means that we will be naming the compound as bute, right? So let's go ahead and consider that. Then we are going to go ahead and write down our functional group. So you can see our functional group is, we're dealing with an alkane. So it will be butane, right? Now, again, our side chain is the same as before. The side chain has 1 carbon atom, so it's methyl. And then finally, we have to now talk about the numbering. Now, in this scenario, it does not matter whether if I count from the right side, I'll get a different number. And if I count from the left side, I will get a different number. If I count from, for example, the left side, I get 1, 2, 3, 4. The methyl group is on carbon atom number 4. But if I count from the right side, I get 1, 2, 3. The carbon atom or the methyl group is on carbon atom number 3. Now what? What do I opt for? What do I choose? Remember this. You will always choose to count from the side that is giving you the smallest number. If I count from the right side, I get number 3. My methyl group is on carbon atom number 3. But if I count from the left side, I am getting number 2. We will always choose the smallest number. So this is going to be 2-methyl butane. And these are the 4 rules that we have in our, that you guys need to go ahead and go over, right? Now, if it doesn't make sense so far, don't worry about it, because I do have questions for you, for us to practice, and you guys will see exactly how we're going to use the rules, right? Don't worry about it. Right now, all I wanted to do was just tell you guys the rules. Now that you guys know what the rules are, I will actually open up some questions for you and we will practice how to go about them. Okay? First of all, we have a compound in front of us. Let's go ahead and start with, and if you guys think you know the answer, if you guys think you can try and solve it out, go ahead and type out your answer in the chat. Okay? Now, if we go ahead and we consider our compound number 2 first. All right. Now, let's go ahead and try to name compound number 2. First thing is first, again, I want you guys to identify, what's the first rule? Longest continuous carbon atom chain. That's rule number 1. Identify the longest continuous carbon atom chain. So, if we identify, at least if you guys think the answer is different, let me know. But this is the longest continuous carbon atom chain. Actually, no. This would be the longest continuous carbon atom chain, right? 1, 2, 3, 4, 5, 6. Right? The longest continuous carbon chain I can make has 6. You might be tempted to also draw like this. 1, 2, 3, 4, 5. So you see, if it's really important to make sure that you are getting the longest carbon chain possible. If I join the carbon atoms in a chain like this, I get 5. But if I draw the carbon atoms in a chain like this, I get 6. So we will choose 6 carbon atoms. For 6 carbon atoms, we use hex. So I'm going to go ahead and write down, when I'm naming my compound, I'm going to write down hex. There are 6. We don't have 7 carbon atoms. 1, 2, 3, 4, 5, 6. Right? We have 6 carbon atoms. So the suffix we normally use for 6 is hex. All right, that's the one that's used most commonly or most generally. You might have heard of it differently from your teachers depending upon what board you're studying from. But for 6, hex is the one that's used most commonly and most widely. This carbon atom will not be counted in the main chain. That's exactly what I'm saying. See, I cannot make a continuous chain that includes this carbon atom and also these 2 carbon atoms, right? Can you do that? Can you make a continuous chain without raising your hand that includes all 7 carbon atoms? You cannot. That's exactly my point. I will not automatically say that this has 7 carbon atoms. It does have 7 carbon atoms, but when naming it, I will not consider 7 carbon atoms. That's why I'm saying we need the longest chain, longest continuous chain, right? This 7th carbon atom cannot be included in my longest chain. The longest chain I can make multiple chains. You can actually make multiple chains, right? I can make a chain like this, but that would only have 4 carbon atoms. It's not my longest chain. I can make a chain like this, but that would have 5 carbon atoms. That is also not the longest chain I can make. If I join all the carbon atoms like this, I get 6. So even though the molecule has 7 carbon atoms, Iman, but I cannot go ahead and name it sept. The reason for that being is because the longest chain I can make that is continuous without breaking my chain is with 6 carbon atoms. So I'm going to write down hex. Okay, after writing down hex, we are going to go ahead and then write down the name of our functional group. Our functional group over here is going to be alkane, right? This is an alkane. So the name is going to be hexane. Now, after that, you are going to identify the side chain. What is the side chain? Is there any side group? Is there anything other than the functional group? Is there any chlorine, any bromine? Is there something else involved? Yes, there is a CH3, right? Whenever we have 1 carbon atom, that's methyl. So when I'm going to be naming it, I'm going to be naming it methyl hexane. So in my entire name, you can see now I have a total of 7 methyl, 1 from methyl and 6 from hexane, total 7. But while naming it, we will not be naming it septane, we will be naming it hexane because the longest chain only has 6 carbon atoms inside it. Last thing that you have to do is you have to number the side chain. Which carbon atom has the side chain? Let's go ahead. Let's figure it out. You can count from the left, you can count from the right. But remember this, that you always choose the side which gives you the smallest number. What does that mean? That means if I count from the right side, what number do I get? I get 1, 2, 3, 4, 5. Sorry, 4, right? Methyl group is on carbon atom number 4. But if I go ahead and remember, we're counting on the main chain. Do not count CH3. Okay, do not count CH3. We're counting the carbon atoms in the main chain, right? So these are the carbon atoms in the main chain. This.
So we're only going to be counting them. So if I count from the right side, I get carbon atom number 4. But if I count from the left side, I get 1, 2, 3, which means that I will choose the side which gives me the smallest number. So when naming this compound, we are going to be naming this methyl hexane. And the number of the methyl group, where is the methyl group located? It's located on carbon atom number 3. So that's how we're naming compound number 2. Now, take a look at compound number 3. Sorry, compound number 12, right? Compound number 12, let's see how we can name compound number 12. If you guys think you know the answer to this, please go ahead and type it out in the chat. I would love to see your answers. Again, what are we going to identify? Step number 1, longest continuous chain. Let's go ahead, consider all possibilities, right? Consider every single possibility and see what is the longest chain you guys can make. So I can make a chain like this, which would be 1, 2, 3, 4, 5, right? I could also go ahead and make a chain like this. I get 1, 2, 3, 4, 5. I can also go ahead and make a chain like this, which would also give me 1, 2, 3, 4, 5. So in this case, it seems like regardless of how I make the chain, do I make a chain straight like this? Do I make a chain like this? Or do I make a chain like this? I have tried all possibilities. So the longest continuous chain, keep in mind it has to be continuous, is with 5 carbon atoms, which means that this is going to be pent. Yes, that's correct. Good job. So this is going to be pent. Then after that, what we are going to go ahead and do is that we are going to identify our functional group. Our functional group is our alcohol group. So this is going to be pentanol, right? The OH group gives us the suffix of -ol. And then just your answer, by the way, the one you've given in chat is almost correct. Almost correct. I'll tell you exactly just one thing that you need to amend. Okay. Now, again, you guys can see that we have got methyl groups, but there's something different to the question we just did. We don't have one methyl group, we have 2 methyl groups. Now, what do we do? What am I going to say now? In this particular case, what am I going to do is that I'm going to write down dimethyl. I'm going to write down dimethyl. What's the reason I'm writing down dimethyl? To show that I have got 2 methyl groups. If I had 3 methyl groups, I would write down trimethyl, right? So over here, I've got 2 methyl groups. So this is going to be dimethyl. That's one thing. So remember this, if you have 2 chlorine groups, dichloro, 2 bromine, dibromo, right? But we have 2 methyl groups, not one. So it's going to go ahead and it's going to be dimethyl. Then coming on to numbering of the carbon atoms. Now, in this question, you guys will not only have to number the methyl group, but also the OH group. Right? How are you guys going to, you guys have to, when you're naming the compound, you have to show the location of all the groups that are found in the molecule. So we don't just need to number the methyl groups, we also need to number the OH group. Now, we can go ahead and count from the left side as well as from the right side. Let's try it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now over here, you guys will be slightly confused. You'll think, okay, the OH group is on carbon atom number 3, but like there's one CH3 on carbon atom number 2 and then the other one on carbon atom number 4 or 2, or now what do we do? Right? Now what are we going to do? Because that was a simple scenario. We had one chain. And now we have got multiple. So now what are we going to go ahead and do? Right? Now, in this condition, remember the functional group has priority, meaning that you are going to choose the number for the functional group.
And for the rest of them, right? For the rest of them, you will follow the same order. Meaning that if you count from the right side and you're getting the smallest number, count from the right side. For all of them, for all the groups, for all the side chains, right? You're not going to count again and again for all of the methyl group, for all of the OH group. No. What you're going to do is that you are going to go ahead and choose either the right side or the left side. Pick one and only use that for all of the groups. What does that mean? That means that, let's say, in this particular case, the OH group is on carbon atom number 3. So it doesn't matter if I count from the right side or the left side. Let's say I decide to count from the left side. 1, 2, 3, 4, 5. Right? When I am going to be naming the compound, right? When I'm going to be naming the compound, I will, for example, I have decided to pick the left side. Normally, you pick the side which gives you the smallest number. But my functional group, because remember, functional group is the important one. We will take a look at the functional group. So the OH is on carbon atom number 3. If I count from the right side or the left side, it's the same. So let's say I decide to go for the left side. Okay. Now, when I am naming the compound, I'm going to follow the same numbering for all of them. You're not going to count again and again and again and again for, okay, what is the number for methyl group? What is the number for the OH group? No. You're going to name the compound like this. This is going to be pent. The OH group is on carbon atom number 3. So you'll write down pent 3 all, pentane 3 all. And then you're going to mention the 2-methyl group. That will be dimethyl. And then you are going to go ahead and number the carbon atoms. So 2 and 4. See, I'm not counting again. I've picked the left side. I'm sticking to the left side for all of the groups, right? You will only count at the start. At the start, you will choose either the left side or the right side, whichever is giving you the smallest number. But once you've chosen the side, please use the same side for the entire molecule. Okay? So this will be 2, 4, dimethyl, pentane, 3, all, right? So that is going to go ahead and take a look. Okay. How is it dimethyl? It is dimethyl because I have the longest carbon atom chain. I am considering this to be my longest carbon atom chain. Okay. 1, 2, 3, 4, 5. It doesn't matter how you take the longest carbon atom chain. If I take this as the longest carbon atom chain, I still get 5 carbon atoms. 1, 2, 3, 4, 5. And again, I will have 2 methyl groups, right? CH3 and then CH3 over here. Again, it doesn't matter if you take the chain to be like this. If you take this as your longest chain, you again only get 5 carbon atoms and 1 CH3 here and 1 CH3 here, right? Then if you take this to be your longest carbon atom chain, 1 here and 1 here. So it doesn't matter how you remember this. It doesn't matter. You should get the same name. That's how you know you're on the right track. So we have got 2 methyl groups. Hence, we're going to be, we're going to be writing it down as 2,4 dimethyl pentane 3 all. That's right, Tia. So that's how you're going to go ahead and write it down. Okay, so these are some of the rules that you have to go ahead and you have to take a look at. I would love to go over this in more detail with you guys. Normally in the class, I do like 2-3 classes on this and we practice how to go over all the questions together. But obviously today we do not have the time to go over it on detail at the end of the session. If you guys still feel confused, inshallah, we'll go over some more questions and we will see exactly how to practice this. If you guys want to take a screenshot of these questions and try to solve them yourself, meanwhile, we can discuss the answers toward the end of the session. Okay? All right. So now we know what are the basic rules for naming our organic compounds, right? Now, Okay, this is an interesting one. We have in front of us a name and we have to figure out what the structure is. So I will draw the structure for you guys for one of the compounds, and the other structure I want you guys to try to attempt it yourself. If you guys want, you can send the answer. You can draw it on a piece of paper, take a picture, send it in the WhatsApp group, and I will get to it towards the end of our session. So first of all, let's take a look over here. I have given you the name. Can you draw the compound? Let's see. First thing is first, we have hexene. I want you to identify hex. Okay?
Hex means 6 carbon atoms. So you will draw 1, 2, 3, 4, 5, 6. Then you can see we have been given ene. Ene means alkene, right? ene is the suffix for alkene. Now, we need to put a double bond. Where do I put a double bond? 2. Do you see how it says 2? The 2 means that we have to put a double bond on carbon atom number 2. Now, it's up to you guys. You guys can either choose the left side or the right side to count. Okay? I'm going to count from the left side. So this is carbon atom number 1 and this is 2. So this is where the double bond will be on carbon atom number 2. Then we have a ethyl group. Ethyl group means that it has 2 carbon atoms, right? So we have to make an ethyl group, but we have to make it on carbon atom number 4. If you have chosen to count from the left side, please stick to the left side for the rest of the molecule. So 3, 4. That means I need to put a ethyl group on carbon atom number 4. So an ethyl group will simply be C2H5. Right? Then you are going to continue. So we have chloro, but it says dichloro. Di means 2. So you have to include 2 chlorine atoms somewhere in the molecule. How do we include 2 chlorine atoms somewhere in the molecule? Quite easy. To do that, all you're going to do is take a look at the numbering. 1 chlorine atom is on carbon atom number 2. And 1 chlorine atom is on carbon atom number 3. So I will make 1 chlorine over here and I will make 1 chlorine over here, right? We stick to the numbering. The numbering we have decided, we're going to stick to it for the rest of the molecules. We don't change the numbering in the middle of the molecule, okay? Now, the rest of it, I am just going to complete the rest of the structure. We know this is an alkene. We know each carbon atom can have four covalent bonds, right? Carbon can make 4 covalent bonds. So 1 covalent bond we have here, 2, 3, 4. 1, 2, 3, 4. There we go.
So this is exactly how you're going to draw 2,3-dichlorohexene. And now the next structure, which is 3-ethyl-4,5-dimethyl-pentane. This I'm giving to you guys sort of as a brain teaser. Okay. Try to draw the
Miss,
structure yourself.
what's
Yes.
on the number 4? Carbon number 4?
Carbon ethyl group. So ethyl, eth means 2 carbon atoms, right? So C2, if you're confused, 1 second, I'll draw this properly. If you're confused, you can draw it like this.
Carbon atom number 1, carbon atom number 2. Okay? And then just draw the hydrogen atoms. This is what I've drawn.
Okay? Ethyl means that you have to attach 2 carbon atoms over here. Okay? So you can just draw normally the way you draw your alkanes, you'll just draw like that. Okay? But it will have 2 carbon atoms. So you can either draw it like this or you can write it down as a short form, which is 2 carbon atoms, 5 hydrogen atoms. So go ahead, take 3-ethyl-4,5-dimethyl pentane. Take this as a brain freezer. Go ahead, see if you can you can solve it, right? And solve it on a piece of paper, send your answers on the WhatsApp group, and we will discuss the answer to this towards the end of the class. All right. So the next thing that we have to go ahead and take a look at is we're going to be taking a look at our hydrocarbons. We're just going, again, keep in mind that um we do not have the time to go over the entire topic in detail. So this will be, in fact, a summary, but I do not expect you guys will be having much problem with it because I'm sure you have gone over that in your syllabus. All right. So first of all, starting about talking about our hydrocarbons, right? As you know, alkanes are considered to be yes, we're going to go over carboxylic acid as well. As you know, hydrocarbons are, quite simply put, organic compounds that only contain carbon and hydrogen inside the molecule. That's it. They have carbon and hydrogen. There will be no oxygen, there will be no nitrogen, there will be no sulfur. Only carbon and hydrogen atoms are a part of it. Then, these are found very naturally and very commonly in our crude oil, right? The general formula for our alkanes is CnH2n plus 2, where the N stands for the number of carbon atoms. So, for example, if I have 4 carbon atoms, my N stands for 4. I will take my 2 multiplied by 4 and plus 2, which gives us the formula C4H10, right? So that's the general formula where the N stands for the number of carbon atoms that you guys have in your question. Then do remember that these are saturated hydrocarbons, meaning that they only have single covalent bond. They do not have they only have single covalent bonds present. That's it. Generally, alkanes are considered to be non-reactive. Remember that. They're pretty non-reactive. It's really hard to get alkanes to actually take part in any reactions, which is good because that means we don't have to study a lot of reactions for alkanes, right? So they're pretty non-reactive. So because they're so non-reactive, which is good for you and me, we only have to study 2 reactions for alkanes. One of them is combustion, which is, I believe, a reaction that you guys have gone over quite a few times. Madiha, don't worry. I will make sure that this presentation is given to you. Okay, we'll provide you with the presentation, so don't worry about that. As long as you understand what's going on, that's fine. Okay, so when we talk about combustion, right? So combustion, pretty easy. What is going to happen that your alkane, whether it's methane is the one that's found quite commonly in our environment, whether it's methane, ethane, propane, doesn't matter. The alkane will react with oxygen, right? In the presence of heat energy. Please keep this in mind that we do need to provide heat energy for a combustion reaction to occur, okay? We need to provide heat energy to get the reaction started because, like I said, please remember alkanes are very non-reactive. They're not going to be reacting with oxygen on their own. We need to provide an incentive, we need to provide a stimulant, and that's heat energy. We'll provide heat energy and methane will react with oxygen and it's going to give you carbon dioxide, water, and of course, it's going to release energy in the process, right? That's a combustion reaction, which I believe you guys probably know pretty well by now. The other reaction is a reaction with chlorine. Okay. Now, keep in mind that alkanes, like I said, pretty non-reactive. So they will not react with chlorine on their own. For this, again, we require some help. And the help that we require is UV radiation, UV light. Whether that UV light is coming from the sun, whether that UV light is coming from the UV lamp um, in your laboratory, it doesn't matter. You just require UV radiation. Now, why is UV radiation so important? The reason you need UV radiation is to break the covalent bond inside the chlorine molecule, right? Chlorine has a single covalent bond inside it. This chlorine single covalent bond has to be broken. Now, when the single covalent bond is going to break, you're going to get a species that we call as free radicals. What are free radicals? Free radicals are chemical species that are like extremely reactive. They are extremely reactive chemical species. So the bond between the two chlorine atoms is going to break, right? Due to the UV light. The UV light is strong enough to break the bond. The chlorine atoms are instead going to become these really reactive species called free radicals. These really reactive species are now able to attack the alkane because alkane is very non-reactive. It's not going to react easily at all. So we need something like free radical. Free radical is so reactive that it can actually go to your alkane molecule and break the covalent bond that is between the carbon and hydrogen. So one of the chlorine free radicals is able to break the covalent bond between carbon and hydrogen. What is going to happen? Why is this happening? The chlorine is extremely reactive. It wants to make a bond. It wants to be part of a molecule. It doesn't want to stay as a free radical. It wants to react with another atom and make a molecule. So what it basically does is goes up to methane and it steals one of the hydrogen atoms from methane. It will say, I'll take one of your hydrogen atoms for myself, right? And it will simply end up making HCl, hydrogen chloride. But we have a problem. The problem is that our methane now has turned into a free radical. The methane carbon atoms have 4 covalent bonds. This carbon atom only has 3. One of the hydrogen atoms has been stolen from it by chlorine. So now we have another free radical, methyl free radical. Methyl because it's carbon, 1 carbon atom, right? This methyl free radical, what is it going to do? It's going to say, you know what? I need 4 covalent bonds. I only have 3. I need to somehow make 4 covalent bonds. So it's going to go to another atom of chlorine and it will say, you know what? I'm going to make a bond with one of you. I'm going to make a bond with one of your chlorine atoms because I want a bond. I don't care. So it's going to make a bond with one of the chlorine atoms and it's going to make chloromethane, right? 1 carbon atom and the side chain is chloromethane. But we have a problem. Again, we have a chlorine free radical, right? We have a chlorine that is now completely free. It has not attached to any bond. This is very important. That's why this is a chain reaction. It just keeps on happening and happening and happening and happening and happening and happening. But the main thing is that in the process, we get CH3Cl. This is a chloromethane. Chloromethane. And when we talk about chloromethane, so chloromethane is a class of organic compounds that we call halogenoalkanes. Halogeno because there's some halogen like chlorine, bromine, iodine, maybe fluorine, and we have an alkane. So these are the only 2 reactions of alkanes that they undergo. They will either undergo combustion, in which case they will give you energy, or they will undergo free radical substitution with chlorine or bromine or iodine. It doesn't matter. But the condition is that UV radiation has to be present. And this is a sort of a chain reaction, right? It keeps on happening and happening and happening and happening because free radicals keep on forming. Other than this, there is not much detail that you guys require to know in your syllabus. Then, when we are going to go ahead and we are going to talk about it. This second compound or the second hydrocarbon that we have to talk about is alkenes, right? Alkenes are actually your hydrocarbons that have a double covalent bond present inside them, right? The double covalent bond is actually found inside alkenes. Now, alkenes have the general formula of CnH2n. Just like with alkanes, the N stands for the number of carbon atoms. Okay, so meaning that if I have 2 carbon atoms, the formula will be C2H4. Now, alkenes are not found very commonly in the environment. All right, they're not found that commonly in the environment. So the process that we generally use for finding or making alkenes is we obtain them from crude oil. Okay. Now, again, I do not have the time to go over fractional distillation of crude oil with you guys. Please do cover it at home if you guys are preparing for your exams. I wish I had you guys join me earlier. We could have gone over the fractional distillation as well. But regardless, that is the method that we use to actually obtain our alkenes. Now, how do we use alkanes to get alkenes? We use alkanes to get alkenes by using a process known as cracking. Because alkenes are not found that commonly in our environment. Alkenes are not found very commonly. So if I want to get my hand on an alkene, then I have to go ahead and I have to use a process known as cracking. What does cracking do? Cracking takes a large molecule, which is your alkene. It takes alkanes and it breaks it down and gives you an alkene. Okay, that's cracking. It's in the name, cracking. You're breaking it open. Large alkanes are useless to us pretty much. We can't get much use out of large alkanes. So what do? Best of both worlds. Take something that's useless or not that useful, which are large alkanes, break them down and make them into something useful, which is alkenes. That process is known as cracking. So in this case, you can see we're starting with C12H6, right? This is known as dodecane. And I can break it down to give me C10H22, which is decane. This is an alkane with 10 carbon atoms. And I get an ethene. Ethene is the alkene that I require. So I can break down a large alkane to give me an alkene. I can perform the breaking of the molecule. I can perform the process of cracking either by using high temperature or by using a catalyst. Okay. When we talk about when we're going to go ahead and talk about it, so either we can go for a high temperature. If I use a high temperature, that is known as thermal cracking. Or if I use a catalyst, the catalyst we normally use is aluminum oxide or silica oxide. So I use one of these, I'm going to go ahead and use it to perform the process of cracking. So either you can use high heat energy, high temperature, or you can make use of the catalyst. Okay. When it comes to alkenes, there are 4 reactions that are important for you guys to know. One of the reactions that's really important for you guys to know is hydrogenation. What is hydrogenation? In hydrogenation, quite simply put, remember how I mentioned that alkenes are unsaturated hydrocarbons, right? What does that mean? That means that they have got a double covalent bond. The double covalent bond means that I can add more molecules in here. That's the reason why alkanes are not reactive, because alkanes, just like, think of it this way, all the bond quota or all the bonds that they have are already occupied. Carbon can make 4 bonds. All the bonds are full. In this case, though, we have a double covalent bond. This double covalent bond can break, and I can add more molecules into this organic compound. So I can perform hydration. in hydration, I can add hydrogen to my molecule. What is going to happen? The double covalent bond is going to break. And as the double covalent bond is going to break, hydrogen atoms will be added to the carbon atoms. What is basically happening? I am taking my ethene and I'm turning it into ethane. I'm taking an alkene and I'm turning it into an alkane, right? Because I just broke the double bond and now all the bonds are single covalent bonds. So took an alkene, turned it into an alkene. That's hydrogenation. The conditions for these reactions are what you guys need to remember. The catalyst we use is nickel and the temperature is around 200 degrees centigrade. Then we can perform hydration. In hydration, I am reacting the same ethene, but I'm reacting it with steam. Again, since I'm reacting it with steam, what is going to happen? That the double bond is going to break. We have steam is water, right? H2O. So we have one OH and one hydrogen. So one carbon atom will receive hydrogen and the other carbon atom will make a bond with the OH. As a result, you will convert your alkene into alcohol. So ethene into ethanol. The condition for this is that you need a catalyst, that's phosphoric acid. The temperature is around 300 degrees centigrade. And the pressure is 60 atmospheres. Then you can go ahead and react it with a halogen, right? You can go ahead and you can react it with a halogen. I have chosen bromine. Why? Because the bromine water test is used very commonly. If you want to test for alkenes, bromine water is what we use. What is going to happen? Same thing as what we just studied. The double bond is going to break and bromine is going to be added on each carbon atoms. In this case, please notice that I am getting dibromoethane, right? If you talk about alkanes, when alkanes react, the product was CH3Cl, right? Over here, we are getting dibromoethane, right? Dibromoethane. And this reaction will happen at room temperature and pressure. This is a test you can use to distinguish between alkenes and alkanes. If you are ever confused, you have a solution in front of you, you're like, oh my God, do I have an alkene? Do I have an alkane? What am I dealing with? What are you going to do? You are going to go ahead and add bromine water to it. If it's an alkane, it will not react in normal room temperature and pressure. It will only react if you have UV light. Alkenes, on the other hand, will react with it even at normal room conditions. And you will actually see that the color of the bromine water is going to change. It's going to go from orange to colorless. The last reaction that your alkenes undergo is polymerization, which we will take a look at as a separate topic. So I'm leaving it here for now. Then some other organic compounds that are really important for your syllabus are your alcohols, carboxylic acids, and of course you have esters. Now, starting with alcohols. Alcohols obviously have the OH functional group, right? They have the OH functional group that is present. Now, when we talk about alcohols, again, there are two reactions that are important for you guys to know, or two aspects about alcohol that are important for you to know. One, you guys need to know how we can make alcohols, especially ethanol. Ethanol is really important. You guys need to know how we can make ethanol, and then you need to know about the oxidation of alcohols. Before we discuss the oxidation of alcohols, let's talk about something that's really important. And you guys will see this in past papers as well. You'll be encountering questions where they'll be asking you, how can we make ethanol? What are the differences in the methods that you have listed, right? So first thing is first, we have two methods that are readily available to us. So when we're going to go ahead and we are going to talking about it, we are going to go ahead. There are two possible methods that we have. One method that we have is we can use hydration of ethene. This is a method that you and I have already, by the way, discussed over here, right? We took ethene, we reacted it with steam, and we got alcohol, ethanol, right? So that's the first method. The second method that we have is fermentation, right? Fermentation is what you do when you take your yeast, you take sugar, you add yeast to it, and yeast is going to convert the sugar into ethanol. So those are the two processes that we have. One, hydration of ethene, and the other one is fermentation. Both have their own advantages and disadvantages. For example, for ethene, we can use hydration of ethene, but ethene is a non-renewable resource. Where do we get ethene from? We get it from our crude oil, right? Crude oil is non-renewable. Fermentation, on the other hand, uses glucose. That glucose you can get from sugarcane. Fermentation, by the way, is the breakdown of glucose to give you ethanol and carbon dioxide. This is the process that happens in baking. So if you go to baking, right, what do? We take glucose, sugar, right? We add in our baking. And in the process, we add yeast, right? Yeast are going to break down glucose to give you your ethanol, which is the alcohol. And along with that, you get carbon dioxide gas. That is why your cakes, your breads, they tend to rise due to the production of carbon dioxide gas. So fermentation requires renewable resources, which is good. Hydration needs non-renewable resources. Hydration is a continuous process. What does that mean is that I do it in an industry. I can start the reaction and I can, continuously supply glucose. I can continuously supply ethene and steam. No problem. I'll add ethene, I will add steam, and I can continuously keep on adding them again and again and again and again with the presence of our phosphoric acid catalyst, and I can make ethanol continuously. Fermentation, though, is a batch process. You have to add in the glucose, you have to add in your yeast, leave it for a few days, come back after a few days. The yeast cannot be reused, so you have to start the reaction all over again, right? Hydration of ethene is a fast reaction. We are using a catalyst, we're doing it inside the lab. It's a fast reaction. Fermentation is a quite slow reaction because obviously the yeast are the ones that have to do the job, so they'll take their time. The hydration of ethene always gives us pure ethanol. There are no impurities. We just get ethanol. On the other hand, fermentation gives us a impure ethanol because obviously it's going to have yeast cells inside of it. It's going to have any waste products that the yeast cells have made. So you're not going to get a very pure solution. Then, so these are some of the major differences that you have between the two methods that you guys need to go ahead and go over. Then another reaction of alcohols that you guys need to know is the oxidation reaction. In oxidation reaction, what are we doing is we are taking our ethanol and we are oxidizing it into ethanoic acid. This is one of the ways of making carboxylic acid. If I want to make carboxylic acid, I can take an alcohol. I can add an oxidizing agent to it, like potassium dichromate, which is an oxidizing agent. And I will be able to oxidize it to a carboxylic acid. Again, we will see a color change. See, the color goes from being orange to green, right? That's the color change that we observe for potassium dichromate, yellow, orange to green. So these are the two things you guys need to know about alcohols. One, how are we going to make the alcohols? What are the two methods? What are their advantages and disadvantages? When we talk about the second reaction is how we can take our how can we go ahead and take our ethanol and convert it into ethanoic acid or any alcohol and convert it into carboxylic acid. And since we just talked about carboxylic acid, right now, ethanoic acid, right? So let's talk about carboxylic acids. What are carboxylic acids? Carboxylic acids are organic compounds that have a very specific functional group that is COOH, right? In fact, let me draw it for you. C double bond OH, right? We have a carbon atom that has a double bond with oxygen and then a single bond with the OH group. This is what we call as our carboxylic acid. So any molecule that has COOH in it, that molecule is going to be known as a carboxylic acid. So do remember that the carboxylic acid is a weak acid. We are going to go over acids and bases in just a bit, but do remember it is a weak acid. So all the reactions that acids undergo, acid can react with alkali, acid can react with metal, acid can react with carbonates. All the reactions you have studied in the topic of acids can all apply over here. So this is a topic that is interlinked with the topic of acids and bases. So you guys might want to study them together. Carboxylic acids and bases. Because the reactions of carboxylic acids are very similar to the reactions of acids because they are going to be acting as acids. So when we are going to go ahead and talk about it, these are some of the common reactions that you guys have to know. And you will notice these are the same reactions that you study in the topic of acids as well. Carboxylic acids can react with metals to give you salt and hydrogen gas. So for example, we have ethanoic acid. Ethanoic acid will react with magnesium to give you magnesium ethonate. Whenever a carboxylic acid becomes a part of a compound, we change the name. We don't write down acid anymore. We write down ate, right? ATE, ate. So if ethanoic acid is becoming a part of a salt, it will become ethonate. If it was propanoic acid, it would become proponate, right? So we have magnesium and we have ethanoic acid. So we get magnesium ethonate, salt and hydrogen gas. Similarly, our carboxylic acids can react with carbonates. And the reaction is the same as we see with acids. Acid plus carbonate gives us salt, water, carbon dioxide. Salt, water, carbon dioxide, right? Same thing that we see with acids. And the reaction, again, notice that the naming is the same thing. I'm taking ethanoic acid and reacting it with sodium carbonate. So when I make the salt, my salt will be sodium ethonate, right? Sodium ethonate, and along with that, I get water and carbon dioxide. Then we can go ahead and also react them with alkali because like I just said, what are these? This is a acid, right? It's going to be acting like an acid. So it's going to react with an alkali. And when it's going to react with an alkali, right? What is it going to give you? Salt and water. Neutralization reaction. Really basic, really easy neutralization reaction. Acid plus alkali is going to give us salt and water. We will get a salt, sodium ethonate, and we will get water. Perfect. And the final reaction of carboxylic acid that you guys need to know about is also ester. One of the topics of our organic chemistry, ester. How do we form an ester? An ester can be formed when I take my carboxylic acid and react it with alcohol. Two compounds that we just studied. If I take a carboxylic acid and I react it with an alcohol, I get a ester. How does an ester form? An ester forms something like this. Let's say that we have methanol. Okay, methanol is going to be CH3OH, right? One carbon atom. Let's go ahead and react with ethanoic acid. In fact, let me draw the displayed formula for you guys so it's as easy as possible. Now, what is going to happen that the hydrogen from the carboxylic acid and the OH from the alcohol, they will combine with each other. So the hydrogen from the carboxylic acid and the OH group from the alcohol will combine with each other and
form a molecule of water. Other than that, what are we going to get? So I will have, I will now join the two compounds. That's what I'm going to do. I'm going to join the two compounds. I will remove the hydrogen and the OH, and whatever is left, let's join it up into one molecule. So I'll copy the molecule as it is. Carbon, double bond oxygen, single bond oxygen, and then I won't write down the hydrogen. I will now move on to the alcohol. In the alcohol, again, OH is not to be included. Why? Because the OH is now a part of the water molecule. That leaves me with carbon and 3 hydrogen. And that's how you're going to draw the ester. And do you see this bond? C double bond oxygen, single bond oxygen. This COO is what we know call the ester bond. This is our ester linkage or our ester bond. And when we are naming the compound, now what about naming the compound? I will tell you a trick. I have taught you guys the rules for naming the compounds. If you guys want to take the time to figure out the name, you can. But let me tell you a trick. For esters, this trick is only applicable to ester. A shortcut. Whenever you guys are naming esters, always first name the carb acid and then write down the name of the alcohol. That's the order for esters. Shortcut. First write down the name of the acid and then the alcohol. So in our case, what is our acid? Our acid is ethanoic acid, right? We have a 2-carbon acid. So I will write down so I'm going to go ahead and I'm going to write down ethonate, right? And then we will write down the alcohol. Now, the alcohol is written down first, okay? Remember this, the alcohol is always written down first. First, we'll write down the alcohol and then we'll write down the name of the acid. So, my alcohol is 1-carbon alcohol. So, I will write down methyl and the name becomes methyl ethonate. That's the trick. Whenever you are naming your ester, whenever you're naming your ester, right? First, write down the name of the alcohol and then write down the name of the carboxylic acid. That's a shortcut. So first write down the name of the alcohol and then the carboxylic acid. So that means my ester is known as methyl ethonate, right? Take a look at the example that we have over here. We have propanol and we have ethanoic acid. So first write down the name of the alcohol. That will become propyl and then the acid. So the acid becomes ethonate. Propyl ethonate. This is, by the way, an esterification reaction is a reversible reaction. And that means that I can combine the alcohol and the acid to give me the ester. But by adding water, I can also reverse the reaction to give me acid and alcohol. The catalyst that I require for the reaction is sulfuric acid. So this is the 4 reactions that you need to know regarding carboxylic acids: reactions with metals, reactions with carbonates, reactions with alkali or bases, and reactions where we are going to be forming our ester. Now, another important point that I believe you guys are wanted to go over, or feel like a lot of people wanted to go over, actually, isomers, right? How do we make isomers? How do we form isomers? Let's take a look at that. When we talk about isomers, so first of all, let's define what isomers are. Isomers are compounds that have the same molecular formula, but different structural formula. Molecular formula means that they will have the same number of carbon atom, hydrogen atom, oxygen atom, nitrogen atom, sulfur atom, doesn't matter. Whatever atoms they will have the same number of atoms. That means they have the same molecular formula. But when you will draw their structure, the structure will be different. Now, oftentimes when you're drawing isomers in exams, you get confused, right? You're wondering if this is the correct possible isomer, yes or no. So
Remember this, the trick to knowing if you've drawn the correct isomer is to name the compound. When naming the compound, if the name of the compound is different from the original compound, you have drawn a correct isomer. But if you're drawing it and you're getting the same compound or you're getting the same name, you have made a mistake. Now, when we talk about whenever you're trying to make an isomer, 3 things you guys can do. First, consider changing the position of the functional group. That's the first thing I want you guys to do. Consider changing the position of the functional group. Okay, functional group is on carbon atom number 1. What if I move it to carbon atom number 2? OH group. What if I move it to carbon atom number 4? Right? First of all, start by changing the position of the functional group. Second thing you can do is make a chain, right? So for example, if I have 4 of these carbon atoms over here, so maybe I can take the CH3 over here, the CH3 that I have over here, and maybe put it somewhere over here, right? That's a chain isomer. I have taken my straight chain and I have made it into a branch. It's no longer a straight chain, it's a branch. The last possibility that you have, and this is a possibility that you guys do not need to actually consider, is that you can have a functional isomer. But chain isomer and position are the 2 ways that you can actually do it. You guys will not find yourself dealing with functional isomers as such. So we will be taking a look at chain and position. We will use these 2 and we're going to practice how to draw our isomers, right? We have a molecular formula in front of us. Top one, C7H16. Let's see how many isomers we can draw. If you guys want to go ahead, please attempt it yourself as well. See how many isomers you guys can draw. If you guys think that I've missed an isomer, let me know in the chat, or if you guys want to draw an isomer and share with me, please go ahead and send it in the WhatsApp group. So one possibility of, we're going to draw as many possible isomers as we can. So one possible isomer that I can do is just draw a straight chain. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? First of all, just go ahead and make a straight chain. Remember, that's always the easiest option. If this is not an option, then go for something more complicated. But if you guys can make a straight chain, make a straight chain and finish the question, right? This is going to be heptane, because this has got 7 carbon atoms. Then let's see what we can do. We can go ahead and we can, obviously I'm not dealing with any functional groups. So changing the position is not much of an option over here. But we can go ahead and we can make some branches, right? Let's see how many branches we can make. One thing that we can go ahead and do is let's make one branch. Right? I can take a methyl group and put it over here. Right? Again, if you guys count the number of hydrogen atoms and the number of carbon atoms, you guys are going to get the same thing. When I'm going to be naming the compound, this compound is going to be 2-methyl-hexane. That's the second isomer I can make. Then, what's the third isomer that I can make? I can change the position of the methyl group. Why don't I try putting the methyl group, let's say, somewhere over on this carbon atom? Now, what am I going to name the compound? I'm going to name my compound I'm going to name my compound 3-methyl-hexane, right? See, you see how the name of the compound happens to be changing as I am going along, as I'm drawing my isomer. If the name of the compound is not changed, meaning that you might have possibly drawn something wrong. What else can we do? So, okay. We took a methyl group, right? We took a methyl group.
why don't, instead of making one carbon atom chain, why not make a two carbon atom chain? Let's try that, right? So instead of adding CH3, let's take two of these carbon atoms and make a chain out of it. Let's do that. Let's make a branch with two carbon atoms. So 1, 2, 3, 4, 5, and maybe I can go C2H5. C2H5 is the ethyl group, right? We have the ethyl group. And obviously, as you can see, this is what? This is now a
Yes, you're right. I have drawn one less carbon atom. There should be another carbon atom over here. So now we are, if we name the second compound that we have just drawn over here, this is going to be ethyl pentane. 1, 2, 3, 4, 5, ethyl pentane. Right? So that is another isomer I can make. Then I can move the position of the ethyl group. So this is 2-ethyl pentane. I can take the ethyl group and I can go ahead and move it to carbon atom number 3. And I can make 3-ethyl pentane, right? So you see, this is how you guys are going to go ahead and you guys are going to be making your isomers. You have lots of option here. That's why I chose a large molecule. You can do dimethyl. You can put one CH3 on carbon number 2, one on carbon number 3. Or you can put both of them on carbon number 3. Or you can put one on carbon number 1, one on carbon number 2, and the other one also on carbon atom number 2, right? So this is how you guys are going to go ahead and you are going to be going over your isomers. This is how you guys are going to be drawing all the isomers. You guys can make so many more isomers of just C7, 8, 16. Just heptane, you guys can draw so many more isomers of this. Take your ethyl group, move it to carbon atom number 3. We discussed it. Make it, you can also go ahead and, like I said, make dimethyl, right? Do dimethyl, put 2 CH3 groups. Change the position of the CH3 groups. Put both of them on carbon atom number 2. Put both of them on carbon atom number 3. Put one on 4 and one on 2, right? Lots of options you have over here. But by naming the compound, you guys will be sure if the isomer you've drawn is correct. So 2 options you guys always have. 1, make a branch. Number 2, change the position of it. Change the position of the branch, change the position of the functional group. Lots of options that you guys have. Now, the last part that we have of our organic chemistry is obviously polymerization, right? It's a really important topic that we have to go ahead and we have to go over. Polymerization, what happens in polymerization? Polymerization is really easy to understand if you think of it in this way, that you have 2 Lego blocks and you're joining them together to make a large tower. That's polymerization. Taking 2 small Lego blocks, joining them together with each other and making a huge Lego tower. Now, in polymerization, there are 2 types of polymerizations that we can have. One is addition polymerization. This is the type that we see with alkenes. So for addition polymerization, we have a criteria. The criteria is the presence of a double bond. If the Lego unit, the Lego block, by the way, the Lego block is known as a monomer and the Lego tower is known as a polymer. If the Lego monomer, the Lego block, has a double bond only then will it give you addition polymerization. If it does not have a double bond, then it is not going to be giving you your addition polymerization at all. So that's number one criteria, double bond, addition polymerization. Now, the good thing about addition polymerization is that it's easy. How is it easy? What is going to happen that the double bond between our two carbon atoms is going to break. And as the double bond is going to break, what will happen that the Lego units will join up with each other. So if my Lego unit is, for example, C2H5, right? The Lego unit will join up with each other with the helping of the double bond, the breaking of the double bond to allow my monomers to attach to each other. And as a result, I will get one long chain, right? This is addition polymerization. Why? Because all the molecules simply added up with each other. Double bond broke and the monomer units added with each other. In this case, this is ethene. Okay? The polymer of ethene is known as polyethene. And polyethene is actually quite commonly used in plastics, right? We have our polythene bags that we use very commonly that are actually pretty bad for the environment. So that's a polymer. Another polymer that we can have is condensation polymer. What is a condensation polymer? A condensation polymer is a polymer in which a carboxylic, not necessarily a carboxylic acid actually, it is when you have got two different monomers. In addition polymerization, we have the same monomer, ethene, 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 ethene. In condensation polymerization, generally speaking, we have two different monomers. So it's two different Lego blocks. And those Lego blocks will join with each other to give you your polymer and also a small byproduct. Small byproduct. In addition polymerization, we only get one product. That's a polymer. That's it. In condensation polymerization, we get our polymer, but we also get a small byproduct on the side, right? A good example of condensation polymerization that you guys have in your syllabus is the formation of nylon, right? Nylon is quite common. It's used for making our clothes, making ropes. A lot of these things are made from nylon. So this is how nylon is actually made. We have a carboxylic acid. Please notice that this carboxylic acid has a COOH group on both sides, right? You have a COOH group on both sides. Hence, this is dioic acid. Why is there a di in the name? That you have two carboxylic acids. So dioic acid, right? This carboxylic acid is reacted with an alcohol. This alcohol also has two OH groups, right? Hence, diol. Diol, because it has got two OH groups that are present. Then, both of them are going to react with each other. And of course, the reaction you guys already know. What is the reaction? Esterification, because I'm reacting an acid with an alcohol. So when I react the acid with an alcohol, what is going to happen? This OH is going to react with the hydrogen of the carboxylic acid will react with the OH of the alcohol. An ester link will form and a molecule of water will be given. Now, this is a simple esterification reaction. So what's all the fuss about? The fuss is that we have functional groups on both the sides. So this molecule can make a bond with carboxylic acid on this side, and this carboxylic acid can make another bond with alcohol on this side. Because you have got functional groups on both sides, so what's going to happen? That they are going to react from both sides. And as a result, you will end up getting a long chain of molecule. And of course, in the process, we're getting a molecule of water. Hence, it is a condensation reaction, right? So in condensation reaction, two different monomers, generally speaking, reacting to give you one large molecule and one byproduct, normally water. And This is the most common one that's mentioned in most syllabus. I believe it's the reaction with the formation of nylon is a part of Edexcel syllabus as well. AQA and obviously Cambridge has it. So this is the common reaction that is in all boards. That's the formation of nylon. If you guys learn this, you guys are pretty much good to go. They're not going to ask you any other condensation polymers in detail. So this is a ester linkage, right? Going to give formation of water. And because you have functional groups on both sides of the molecule, they can join with each other to go ahead and give you a large chain of your polymer. So this was basically what we had to do regarding our organic chemistry, right? Now, let's go ahead and take a look at one example question on the topic. Hold on 1 second. If you guys have any questions, you can go ahead, list them on the chat. I will try to go over them as much as I can. Otherwise, you can ask them towards the end of the session as well. You can do that if you prefer, whatever you guys want to do. Madiha, have stopped the PowerPoint for a second because I just wanted to go over a quick question with you guys. Madiha, you will be given the access for it towards the end of the class, and that's where it's going to be uploaded. All right. So this is a question that we have. Alkenes are unsaturated hydrocarbons. They show structural isomerism. Alkenes take part in addition reaction and form polymers. Structural isomers have the same molecular formula but different structural formula. So they are saying, give an example of structural isomerism. They have left it quite open for us. We can choose our own molecular formula and we can draw the structural formula ourselves as well. So let's go ahead and take a look. The structure that we're going to go ahead and draw is going to look like this. Let's go ahead and take C4H8. Okay, this is butene. We need to draw two structure formula or two isomers of butene. So let's see. One possibility, what did I tell you guys? Always try make the basic structure first. So this is the basic structure. Always count your carbon, hydrogen, oxygen to make sure that you're following the molecular formula. Now I have multiple options. Option number 1, change the position of the double bond. See, my structure has changed. I just went from having but1ene because the double bond was on carbon atom number 1 to but2ene. Now it's on carbon atom number 2. If you want, you can possibly add a methyl chain to it. If you want to do that, you can do that. Right? What if I put a CH3 over here? Now, what do I have? I have propene. I have 2-methyl propene, right? So that's exactly what I meant. The step number 1, change the position of the functional group. That is done. Make a chain, make a branch. You want even more isomers? Change the position of the branch. Try putting it somewhere else, right? So that's how you guys are going to go for your isomerism questions. Now, for this question, I want you guys to go ahead and tell me what you guys think the answer is. Ethene reacts with each of the following. Give the name and structure formula of each product. Steam. In fact, It's not mentioned in the question, but I also want you guys to tell me what is the condition, what are the catalyst, the temperature. What is going to be my product? Can somebody please tell me that first? If ethene will react with steam?
Alcohol.
Yes, you will get an alcohol. You are going to get ethanol, right? Specifically ethanol. So if our alkene is going to react with steam, you're going to get an alcohol, which is going to be ethanol. Okay. I will draw the structure of ethanol for you guys, but can somebody please go ahead and tell me what is the catalyst or the conditions that are required for the reaction?
Phosphoric acid.
Yes, correct. You require phosphoric acid, and along with that, we need high temperature and pressure as well. So that is the catalyst. That's the main thing that you guys need to know. Now, next they're saying hydrogen. What happens if I take ethene and I add hydrogen to it? What's the name of my product? So if you take your you're doing hydrogenation, right? And you are taking ethene, alkene. What happens if you add hydrogen to alkene? What happens if I add hydrogen to it? Yes, it is going to be ethene. The double bond is going to break, the hydrogen is going to be added to it, and my ethene is going to turn into ethane. And the conditions that we require for it is that you need a nickel catalyst to be present. So now this is basically the kind of questions that you guys are going to be encountering in your past papers. The conceptual portion of this is naming your organic compounds, knowing how to draw your isomers, and knowing how to draw your polymers. Other than this, going over the rest of the topic, you have your chemical reactions. So when you're preparing for the exam, do make sure that you guys go over your chemical reactions, because a major part of organic chemistry is writing down those reactions, drawing the structures, knowing what the conditions are. What I will advise you guys is, this is my tip, you can say, for preparing well for your exams. Please go ahead and just take a sheet of paper and list down, or while you're studying organic chemistry, list down all the reactions on that piece of paper. Okay? This way you will have sort of like a cheat sheet. You can't take it in the exam, but it's going to be a piece of paper with every single chemical reaction on it. That's going to make it easy for you to, one, remember them, and secondly, when you're solving past papers, they're going to be really helpful in figuring out what you're dealing with. Okay? So in your organic chemistry, this, you guys can practice making isomers. You guys can practice naming it. But learning the chemical reactions is really important. So do make sure you take the time out to learn the products of each reaction, as well as what are the conditions required for it. Okay. Now, the next thing that we are going to go ahead and target is another really important topic, and that's acids, bases, and salts. Now, again, we can't go over the entire topic in detail, but I have tried to get as much information as I can in a very small amount of time. So let's encounter our acids, bases. Okay. When it comes to acids and bases, one thing that you guys are going to find yourself often answering in past papers is how to define it, right? They'll ask you, what is an acid? What is an alkali? What's a base? And it's a pretty, I mean, it's an important question, because if you guys ever decide to study chemistry in detail, you'll see that there are actually a lot of different definitions for acids and bases. There's one definition that is mentioned in your syllabus. It is suggested by two scientists, two chemists, Bronsted and Lowry. These are the two chemists, and they are the ones that actually came up with these definitions. They said that acids are substances that act as proton donors, meaning that they have the ability to lose or donate a hydrogen ion. They have the ability to lose or donate a hydrogen ion. So any substance that can possibly donate hydrogen ions is going to be known as a proton donor. A base or an alkali, now again, we can give different definitions. I can say an alkali is someone who produces hydroxide ions, OH ions, right? But the definition that was suggested by these chemists was that bases are substances that can act as proton acceptors. So acids are the ones that are producing protons. What are protons? Hydrogen ions. Hydrogen ions are considered to be protons. Why? Well, the reason for that is because hydrogen ions only have a proton, right? Because hydrogen atom only has one electron and a proton. Now, what happens is that it loses that one electron, so you're left with proton. So, any substance that can donate protons is an acid. Any substance that will be accepting those protons is a base. So, hydrochloric acid can donate hydrogen ions. Sodium hydroxide can accept those hydrogen ions. So, hence, it is considered a base. Now, we have certain substances which are known as amphoteric substances. Amphoteric substances are substances that can one second. So, amphoteric substances are substances that can act both as a possible acid as well as a base. They can do both. They can donate hydrogen ions and they can accept hydrogen. And a very good example of this is water. Water can act as an amphoteric substance. If I add an acid to water, water is going to start acting as a base. If I add a base to water, water will start acting as an acid. So that kind of a substance is known as an amphoteric substance. If I add hydrochloric acid to water, what's going to happen? Hydrochloric acid is a proton donor, right? It's an acid. It will produce hydrogen ions. Water will accept those hydrogen ions and become a positive ion. On the other hand, right, if I take the same water, but I add ammonia to it, ammonia is an alkaline gas, right? Or if I want to add ammonia solution, it's an alkaline solution. That same ammonia, now what is going to happen? Look, water has donated its hydrogen ion to ammonia, and now it is OH minus. The hydrogen ion, the H plus is gone. That H plus has now gone to ammonia, and ammonia has gotten a positive charge. It's gone from being NH3 to NH4 plus. It's gone from being ammonia to ammonium ion. In reaction number one, water was the one that was accepting the hydrogen ions. It was acting as an acid. Sorry, it was acting as a base. It was accepting the hydrogen ion. But in this case, it is now losing those hydrogen ions and it's becoming a OH. That's it. It's lost the hydrogen ion. Now it's acting as an acid. So substances that can act both as an acid and a base are considered to be amphoteric substances. Now, another really important portion of this topic is to be able to identify strong acids, weak acids, strong bases, and weak bases. What are strong acids and weak acids? What is it all about? Strong acids are acids that will completely ionize to give you hydrogen ions. Meaning that when they're going to break down, right? When they're going to break down in water and they'll be ionizing, they're going to be producing all those ions, they're going to break down completely. Whatever hydrogen ions they have, they will just release all of them. They're not going to keep any hydrogen ions for themselves. Whatever hydrogen ions they have, they're going to release all of them. A weak acid is an acid that will only release some of the hydrogen ions, not all of its hydrogen ions. It will only release some of those hydrogen ions. When we define it in the exam, what do we say? It partially ionizes. It partially dissociates, partially breaks down. It's not going to be breaking down completely. Keep in mind that weak acids generally give us reversible reaction. Okay? In the process, I will be producing hydrogen ions, obviously, but the hydrogen ions are not going to be completely disassociated, meaning that some of the hydrogen ions will actually still be a part of the acid. So the acid is not going to give up all of its ions. It'll say, I'll give up some of them, but not all of them. So that's a weak acid. Now, strong acids that you guys have in your syllabus are, you have hydrochloric acid, HCl, obviously sulfuric acid, nitric acid, right? These are some really, the list is actually a bit long, but these are some really common ones that you guys are going to see in your syllabus that I believe you guys all are going to be encountering. In weak acids, generally all your carboxylic acids are considered to be weak acids. All carboxylic acids are weak acids. Other than this, carbonic acid, phosphoric acid, all of these are considered to be weak acids. Now, when we talk about our base, right? Now, the base, exactly the same constant. The acid was breaking down to give you hydrogen ions. An alkali, when it's going to break down, it's going to give you hydroxide ions. So any base that is going to, any alkali that is going to break down completely to give you hydroxide ions, like it'll be like, okay, just take as many hydroxide ions as I have. That's a strong base. Any base that is only going to ionize partially, it'll be like, listen, you can take some of them. I'm going to be holding on to the rest of them. That's a weak base. Strong base is your group 1. What's in your group 1 of the periodic table? Sodium, sodium hydroxide. Potassium, potassium hydroxide, right? Lithium, lithium hydroxide. Generally, your group 1 hydroxides are all considered to be pretty strong bases. When it comes to weak bases, so the weak base that we have, again, we have a long list. The most common one is ammonia. Ammonia is a weak base that is included quite commonly. Quite commonly in all of your syllabus, and it's used quite commonly as well, right? So other than that, water is also considered to be a weak base. Then obviously we have other metal oxide, for example, iron hydroxide, and a lot of others, which are all considered to be weak bases. Now that we understand these important definitions, a really important topic that you have to talk about are the salts, right? You guys should know, first of all, please make sure you guys know which salts are soluble and which salts are insoluble. This is something you guys need to know. Once you guys know which salts are soluble and insoluble, then you guys will be able to actually go ahead and actually go over the how to go about making of the salt, right? Because you often see it in the exams questions. How are you going to make a salt of this? So first thing, you should know what type of a salt is it. My suggestion to you guys, learn the soluble salts and everything else is insoluble. That's what I do. Remember this, everything else is insoluble. For example, all nitrates are soluble. It doesn't matter. Is it potassium, magnesium, ammonium, calcium, aluminium, iron? Doesn't matter. Copper, zinc, chromium, manganese, doesn't matter. If it's a nitrate, it's a soluble. If it's a nitrate, it's soluble, right? We automatically learn this. Second rule, all salts of potassium, sodium, ammonium. If a salt has potassium, sodium, or ammonium, you do not need to look at anything else. It's soluble, automatically soluble. Sodium hydroxide, soluble. Potassium nitrate, soluble. Ammonium chloride, soluble. It does not matter what the negative ion is. Sodium carbonate, soluble. Ammonium carbonate, soluble. Potassium carbonate, soluble. It does not matter what the negative ion is. As long as you have potassium, sodium, ammonium, automatically you will say this is a soluble salt. Then, all chlorides except for three, lead, silver, and mercury. Learn the exceptions. Lead, silver, and mercury. That's the only one you guys need are insoluble. Anything other than that, magnesium chloride, aluminum chloride, calcium chloride, doesn't matter. It's soluble. Only three exceptions: lead chloride, silver chloride, and mercury chloride. And this rule applies, by the way, to all halogens. Chlorides, bromides, iodides, they're all soluble except for lead, silver, and mercury. Similarly, all sulfates are soluble except for three: lead, barium, calcium. Calcium sulfate will not dissolve, barium sulfate will not dissolve, lead sulfate will not dissolve. Anything except for this magnesium sulfate, lithium sulfate, iron sulfate, copper sulfate does not matter. They will all be soluble. Then so these are all your soluble salts. Anything other than that automatically becomes an insoluble salt. Now, there's one thing that we have to remember. In the insoluble salt list, there's one thing that I want to add. Carbonates. All carbonates are insoluble. Remember that. All carbonates are insoluble. They do not dissolve, except for three of them. What are the three? These three: potassium, sodium, ammonium. If you have potassium, if you have sodium, if you have ammonium, the salt is going to dissolve. The salt is going to dissolve if you have potassium, sodium, or ammonium. So all carbonates are insoluble except for these three. Except for these three, every single carbonate is insoluble. So hopefully this makes it easy for you. Nitrates, soluble. Chlorides, all soluble except for three: lead, silver, mercury. All sulfates, soluble except for lead, barium, calcium. All carbonates, insoluble except for sodium, potassium, aluminium. Learn the exceptions. Everything else is soluble. Now, after you have identified, so now you have sitting in the exam and they put a question in front of you. They say, how are you going to prepare the salt? What's the first thing I want you guys to do? Identify what the salt is. Do you have a soluble salt or do you have an insoluble salt? That's the first thing you guys will do. So you identified, okay, the salt given to me is a soluble salt. Okay. Now you have four options. There are four methods that you guys can pick. Choose whichever method you like. Method number one. You can take the acid and you can directly react it with metal. Let's say that you guys want to make magnesium nitrate. So you will say, okay, I will take magnesium metal and react it with nitric acid. Acid and metal always give us salt and hydrogen gas. If you guys remember this rule, that metal plus acid gives us salt and hydrogen gas, it'll be much easier for you guys to solve your questions. Okay? Metal plus acid gives us salt and hydrogen gas. That's the first thing you guys can do. So in this case, I will get my salt, magnesium nitrate, and hydrogen gas. Then let's say that this is an option that you guys do not want to take. You want to go for a different route. You can take a metal carbonate and then react that with the acid. So for example, I wanted to make copper nitrate, soluble salt. So I can take my copper carbonate because I want a copper salt, right? So I will take copper carbonate. I will choose nitric acid because I want nitrate. So I will choose nitric acid. For copper, I will choose copper carbonate. And I will always get salt, carbon dioxide, and water. Again, you can learn this. If you take a metal carbonate and react it with an acid, and this is the same reaction we studied for carboxylic acid as well, you get salt, carbon dioxide, and water. So if you take your copper carbonate and react it with nitric acid, we get copper nitrate, carbon dioxide gas, and water. Similarly, we can also do a neutralization reaction. And this is really good for really reactive metals. For example, sodium is very reactive, right? So if you directly react sodium with any acid, it's likely going to cause an explosion because that's how strong the reaction is. So in these cases, going for a titration, going for a neutralization reaction is a very good idea. You can take your hydrochloric acid, react it with sodium hydroxide. You'll get salt and water, sodium chloride and water. Final option is take the acid and react it with the metal oxide. Remember, please remember, metal oxides are all solids, okay? They're insoluble, they do not dissolve. So I can take hydrochloric acid and I can react, for example, with copper oxide. So I will get copper chloride and water. Similarly, if I wanted to make magnesium chloride, I could use magnesium oxide. I would get magnesium chloride and water, right? So I can also take an acid and react it with a solid metal oxide and it will give me salt and water. So when it comes to soluble salt, you can, the acid is the common thing. And then you can react the acid with different things, either directly react with metal or with some carbonate or with an alkali or with an oxide, doesn't matter. Any of these four possibilities will give you your salt. If you want to make an insoluble salt, so for the insoluble salt, the method that we use is that we want to use two soluble salt. Take two soluble salts. Do not take a solid and then add it into a solution and make an insoluble salt. No. You are going to take two solutions. The salt has to be in a solution form. That's the criteria for making an insoluble salt. Both have to be in a solution form. Both salts. Whatever reactants you're taking, please make sure they're in a solution. They're soluble. So for example, I want to make barium sulfate. Barium sulfate, you and I both know that barium sulfate is a insoluble salt. All sulfates except for lead and barium. So barium is a insoluble salt. So I want sulfate ion and I want barium ion. So choose one compound with barium in it and one compound with sulfate in it. For barium, I can go ahead and I can use barium chloride. We know barium chloride is soluble. For sulfate, I can use sodium sulfate. Sodium sulfate is also soluble. Both of them will be in a solution form. So I will react with them with each other and I will get barium sulfate and sodium chloride. And in the process, a white precipitate will be seen of barium sulfate because the barium sulfate is an insoluble salt. Because it's insoluble, so obviously when it's going to form, it will turn into a solid. And that solid will be seen as a white precipitate. And this is actually the test for your sulfate ions that you guys might have studied. Now, once you have the salt, you also need to obtain the salt. You need to separate it out from the rest of the components, right? How do we separate the salt once it's ready? For the soluble salt, we use crystallization method. For the insoluble salt, we use the precipitation method. The crystallization method, how is that done? Quite simply put, we take our evaporating dish. Inside the evaporating dish, we add our solution, okay? After we have added our solution, we are going to slowly heat it up. Please keep in mind, we heat it up slowly. We do not heat it up, like just get rid of all the water. Just put it on a high flame and get rid of all the water. No, we're going to heat the water slowly and explain why in just a bit. We'll heat the water slowly. We will keep on heating it until the solution becomes saturated. Please do not evaporate all of the water, or in the exam write down that we are evaporating all of the water. No. You will heat it until the solution becomes saturated. Once the solution is saturated, you will allow it to cool down. And when it's going to cool down, automatically you will see that the crystals of your salt are going to form. For an insoluble salt, the method is quite easy. It's precipitation. You'll take your funnel, you will take your filter paper, put the filter paper on top of the funnel, pour the solution, let the solution drip down. The insoluble salt, because the insoluble salt is solid, right? It will collect on the filter paper. The rest of the solution will collect in the beaker, and there you go. You have separated out your salt from the remaining components. Now, when we talked about the soluble salt, I mentioned to you guys that please do not get rid of all of the water. What's the reason for that? Why am I asking you guys not to get rid of all of the water? There's a logic for that. The logic for that is this. The crystals of soluble salt. So let's say that I have, for example, copper sulfate. This is a crystal. Now, a crystal of copper sulfate is not just going to be copper sulfate on its own. No. If it's in the form of crystal, it will have some molecules of water present. If it's in the form of a crystal, it will have some molecules of water present. Now, those molecules of water present are known as water of crystallization. Right? We call them water of crystallization. Why? Because they're essential. If I want my salt to be in the form of a crystal, I need these water molecules. Otherwise, my salt will not be in the form of a crystal. That is known as water of crystallization. This is why you want to heat it slowly. You don't want to lose all the water. If you lose all the water, then you won't get crystals. No, you'll get a powder. That's why we're not getting rid of all the water, because the water of crystallization is important. Since the water of crystallization is important, so we cannot go ahead and get rid of all of it. Okay. If I get rid of all of the water of crystallization, so instead of getting a crystal. So for example, a crystal of copper sulfate is blue in color, beautiful blue in color. But if I remove all of the water, so instead of getting blue crystals of copper sulfate, I will get a white powder. Why? Because I have gotten rid of all of the water of crystallization. So this is the reason we do not heat it for until all of the water has been removed. Okay, so now the major thing, another major thing that you guys are going to be going over, again, we're not going to be going over our your ATP practical portion, because we are pretty short on time. Normally we do classes on how to for our regular students, we do classes where we go over the practical portion. We go over how to solve your paper 6 as well, all the experiments that you need to know, how you're going to when you're, for example, identification of salts, right? So how are you going to identify the salt? We go over that, but we do not have the time for that today, so we will not be covering all of that. But just wanted to go over the basics of titration, because titration, again, is really important. You get mole calculations on it. So titration is generally done when I do not know the concentration of an acid or an alkali. Doesn't matter. If I do not know the concentration of an acid or an alkali, I am going to be performing titration. How is titration done? I will take, for example, let's say that I want to find out the concentration of HCl. Okay. I provide you guys sodium hydroxide and I say, listen, you guys, here, have some sodium hydroxide. The concentration of sodium hydroxide is this much. I know the concentration of sodium hydroxide. But I say, I have this acid lying about. I don't even know what the concentration is. Can you guys find out? You'll say, sure, no problem. I'll do a titration. You will fill up the conical flask with the known solution. So the known solution is sodium hydroxide. We know what is the concentration of sodium hydroxide. So you'll fill that up in the conical flask. The burette, we will fill up with the unknown. So we don't know the concentration of the acid. I'll fill it up with the burette. Generally, I will take 25 dm cube of, or centimeter cube actually, of sodium hydroxide. Okay. We can measure the exact volume 25 centimeter cube by using a pipette. This is a pipette. So I use a pipette and it will allow me to exactly take 25 centimeter cube. I add it to the conical flask. I'll follow it up with an indicator. You have multiple indicators in your syllabus. Do make sure you go through them. Open up your burette. Let the drops fall one by one. And then the moment the color changes, you'll close the tab and you will note down the value. After noting down the value, what are you going to go ahead and do? You are going to go ahead, and that is going to be your you're going to use that for mole calculations. If we get the time, I will go over a question with you guys on how to do the mole calculations on titration. So titration is a method that we go ahead and we see quite commonly. Now, so acids, your another major topic aside from acids and bases is obviously we have our periodic table, right? Now, in our periodic table, you can go ahead and divide the periodic table into three portions. We're going to study it in three portions. We have metals, we have our transition elements, and we have our halogens. Now, first of all, some quick rules about the periodic table. Coming on to the periodic table, please do remember that the group number, what does the group number tell you? The group number always tells you the number of electrons in the last shell, the outermost shell, the valence shell. If you guys are ever, like solving your past paper questions, they ask you how many electrons in the outer shell of iron, or how many electrons in the outer shell of aluminium. You guys don't worry about writing down the entire structure of the atom, electronic configuration. It's in period number 3, group number 3, it's got 3 valence electrons. Similarly, for our period, right? The period is always going to tell you it's always going to tell you what? It's always going to go ahead and tell you the number of shells. So if you have any, for example, rubidium. Rubidium is in period number 5. So how many shells is it going to have? It's going to have 5 shells. Group number 1 and group number 2 are known as our alkali metals, right? Then after our group number 2, we have our transition metals. And then from group number 4 onwards, we have non-metals. Now, let's quickly go over the properties that we see with metals and non-metals. Now, when we go ahead and we are going to talk about it, metals have high melting points and high boiling points, right? I think we all know that. What is the reason that metals have high melting point and boiling point? The reason for that is something known as metallic bonding. What is metallic bonding? Metallic bonding is the electrostatic force of attraction between the positive ions and the sea of delocalized electrons. That's the structure in metals, right? That's the structure of metals. You have positive ions surrounded by sea of delocalized electrons. So positive ions, the attraction, the electrostatic attraction between positive ions and sea of delocalized electrons is known as metallic bonding. So metallic bonding is the reason because it's quite strong. So they have high melting point and high boiling point. Non-metals, on the other hand, tend to have low melting and low boiling. Okay? The reason for that is, again, so when it comes to non-metals, we have 2 criteria. We can either have giant covalent structures or simple molecular structures. Simple molecular structures have low melting points and boiling points, but large giant covalent structures like diamond, like graphite, they all tend to have pretty high melting and boiling points. Then metals are shiny, while non-metals are quite brittle. Metals are malleable and ductile. Non-metals, again, are not malleable and not ductile. What is the reason that metals are malleable and ductile? What does malleable mean? If I apply a force, I can turn a metal into any shape I want. I can make a pot, I can make a pan, I can make a helmet. Ductile means that I can use them to make a wire. Copper wires are used very commonly in our circuits. So they can be malleable or they can be ductile. Metals, on the other hand, if you apply a force, they're probably going to break on you. What's the reason? The reason for that is that in your metals, when you apply a force, what happens? That the layers of positive ions, we have positive ions, right? The layer of positive ions can easily slide on top of each other. Okay? Now, another property of metals is that they're good conductors of heat and electricity. Non-metals do not generally conduct electricity. Keep that in mind. Non-metals do not conduct electricity, but graphite does. There are exceptions to everything. Graphite does. Silicon is also, by the way, a conductor of electricity. It's a semiconductor. Silicon and graphite can. They also, non-metals do not conduct heat, but diamond does. Diamond is the exception. Diamond is a wonderful conductor of heat. No, metals generally make ionic compounds. Non-metals can make both. They can make ionic compounds as well as covalent compounds. If a non-metal reacts with a metal, it will make an ionic compound. If a non-metal reacts with a non-metal, it will make a covalent. Then, again, what do you guys need to know? Now, let's quickly go over the reactions that we see with group 1 and group 2. First thing is first, group 1 metals can react with oxygen to give you a salt. Technically, you can call it a salt, lithium oxide. For example, lithium will react with oxygen to give you lithium oxide. Sodium will react with oxygen to give you sodium oxide. Calcium will react with oxygen to give you calcium oxide. Now, there's an interesting thing over here. You need to provide heat energy. Okay? So generally what do we do is I'll take a piece of metal. I'll put it on top of a flame because I need to provide heat energy. And in the presence of that flame, my metal will react with oxygen and give me my oxide. But another interesting thing that's going to happen, the change in the color of the flame. Each metal will give you a different color. For example, sodium gives you a yellow color flame, while potassium gives you a purple color flame, right? So different metals are going to give you different colored flame. Calcium gives you an orange color flame. Different metals are going to go ahead and give you different colored flames. That is their characteristic feature. And if you guys are ever stuck and wondering how to identify a metal, you can always try the flame test. The color of the flame, as the metal reacts with oxygen, it will give a characteristic color to the flame, will help you identify what exactly the metal is. Then, another important reaction is the reaction of those metals with water. Now, in the reaction, we generally get alkali and hydrogen gas. We get an alkali, a base, and hydrogen gas. You guys can learn it. That if we take a metal and we react it with water, we will get an alkali and hydrogen gas. Now, in this reaction, there are certain observations that you guys need to go ahead and you guys need to know about. The observations are that, number one, you are going to see a lot of bubbling and fizzing and effervescence, like anything. Like, it's going to be bubbling literally, like anything. You're going to be seeing so much bubbling and fizzing and effervescence. Now, the reason you're seeing bubbling and fizzing is because of the production of hydrogen. The hydrogen gas being produced is going to give you a lot of bubbling and fizzing and then you will see that the piece of metal is going to be floating on the surface of the water. Why? Why is it floating? Because it has got low density.
And it's going to be literally running around. It's literally going to be moving on the surface of the water. Why? The hydrogen gas that's being produced, right? The hydrogen gas that's being produced is going to cause it to move from one side to other. And then if you decide to test the solution once there is, so you will see slowly the piece of sodium will get smaller and smaller and smaller and smaller, and then it will disappear. And if you decide to test the solution towards the very end, you will see that the pH of the solution will be alkaline. So that was about group 1 and group 2. Then let's go ahead and talk about group 7. Okay, one thing again I want to add over here for group 1 and group 2. In group 1 and group 2, please remember that reactivity increases as we go down the. Okay, what does this mean? This means potassium is more reactive than sodium. If you throw sodium in water, I told you guys what will happen. If you guys throw potassium in water, potassium will actually catch fire. That's how reactive it is. Right? So reactivity increases down the group. Why though? Why is that reactivity increasing? The reason for that is the increase in the number of shells. Right? Group 1 and group 2 make positive ions, +1 and +2. How do you make positive ions? By losing electrons, right? That's how you become positive ions, you lose electrons. So think of it this way. The larger your atom, right? The larger your atom, the further away the electron is going to be from the nucleus. This is lithium and this is sodium. Okay? Now, look over here. This is the nucleus in the center. For lithium, this electron is closer to the nucleus, right? Because it only has one shell in the middle. For sodium, the same electron is further away from the nucleus because it is on shell number 3. Sodium, lithium, potassium, when they react, they lose electrons because they become positive. So for lithium, it's going to be slightly harder to lose the electron. It's not going to give up the electron very easily. When it's making an ionic bond, it's not going to give up the electron very easily. Why? It's going to be like, listen, no, I have got a good hold on the electron. The electron is close to me right now. The nucleus is not going to let go of it. But in sodium, the electron is now a bit further away. So if the electron wants to go away, right? If the electron wants to go away, it can. For potassium, 4 shells. There are more shells present. So the outermost electron is even further away. So it is even easier for potassium to lose the electron and take part in the reaction. So reactivity increases. But for our group 7, for halogens, it's the opposite. Reactivity decreases. If you guys go down the group, it's not going to increase, it's going to decrease. So always keep this on your fingertips. For group 7, reactivity decreases. Reactivity becomes less. But why? As we go down the group, the number of shells increase. Same thing that I just said about metals. But why? Why are they becoming less reactive, but they're becoming more reactive? Same thing is happening. They're both increasing in terms of number of shells. The reason is that group 7 makes a negative ion. So they have to gain electrons. If they want to become a negative ion, they have to gain electrons. Now, what's going to happen that for fluorine, the outermost shell is close to the nucleus. But for chlorine, the outermost shell is further away from the nucleus. So if fluorine wants to gain an electron, if fluorine wants to take an electron and become negative, it's easier for fluorine because the nucleus can quickly pull those electrons towards itself. But for chlorine, the same electron is pretty far away, right? Because you've got so many shells in the middle. So for chlorine, it's harder to pull the new electron towards itself and become negative. So what's going to happen? Your chlorine is basically going to end up becoming it's going to be harder for it to become a negative ion. So please keep this in mind.
As you go down the group, for metals, they will become more reactive, but non-metals will become less reactive. Now, for your halogens, this is a really important table I've put in front of you guys. This is the displacement reactions that they undergo. What is a displacement reaction? In a displacement reaction, a more reactive halogen can displace a less reactive halogen. So, for example, if I react my chlorine with potassium bromide. Now, chlorine is more reactive than bromine, right? How do you guys know? Because it is higher up in the periodic. For group 7, the reactivity decreases. As you go down, reactivity decreases. Bromine is less reactive, chlorine is more reactive. So, what is going to happen? Since chlorine is more reactive, it can displace, it can remove bromine from its compound. It can displace, remove bromine from its compound. And it will give you potassium chloride and bromine. Right? And you will observe a color change. That's why I put this table in front of you. The observations are important. So if I take potassium bromide and I react it with chlorine, what will happen? Chlorine will displace bromine because chlorine is more reactive. It will give you the products are going to be potassium chloride and bromine. As a result, you will see that the color of the solution, it will go from colorless to yellow-orange color because bromine is being produced. Similarly, if I take chlorine and I react with potassium iodide, so chlorine is more reactive than iodine as well. So it can displace iodine from the compound. It will remove iodine from the compound. And you will get potassium, chloride, and iodine. And the iodine is going to be visible in the form of a brown color. Now, so these are the observations that you're going to go ahead and see. Now, other than that, when we talk about displacement reactions, so you will also study displacement reactions when it comes to your metals. Okay? When it comes to your metals, what are we going to see? We are going to see that a more reactive metal can displace a less reactive metal. So for example, magnesium can displace copper from its compound. Why? Because magnesium is more reactive. So quite similar to halogens. That's why I put them side by side. These topics link up. Magnesium will remove copper and you will get magnesium oxide and copper. Right? And this topic is related to your reactivity series because while you look at the question, you might be wondering, how are we going to know that magnesium is more reactive or how are we going to know that copper is more reactive? You will know it because of the reactivity series. I have gone ahead and put this table for you guys. This is a summary of every reaction. If you are reacting a metal with oxygen, you will get an oxide, right? That's the reaction I told you guys over here as well. Lithium plus oxygen gives us lithium oxide. Sodium plus oxygen gives us sodium oxide. So I will get an oxide. From potassium to zinc, the reaction is very vigorous. You'll put it in the you'll put it in the Bunsen burner. It will literally burst into flames and it's going to give you a very vigorous reaction. Iron, on the other hand, and if you go down from iron to copper, they react very, very, very slowly. And silver and gold will not react at all, right? So this is your reactivity series. Reactivity decreases down the group, okay? This is the reactivity series and reactivity decreases down the group. Potassium and sodium react with cold water, by the way, and they give you sodium hydroxide and potassium hydroxide. But your calcium, magnesium, aluminum, zinc, they don't react with cold water. They will not. Their reactivity is less. They will not react with cold water. If you want them to react with water, you will have to turn the water into steam. That's how non-reactive they are. And interesting thing, the reactant is the same, water. But when the water is cold water, the product are a hydroxide. You get sodium hydroxide, potassium hydroxide. But when the reactant is hydrogen, okay, when the reactant is hydrogen, what is going to happen? That the product is not going to be hydroxide. The product is when the reactant is steam, I'm sorry. When the reactant is steam, the product is not going to be hydroxide. The product is going to be, for example, if I react magnesium with steam, I get magnesium oxide and hydrogen gas. Okay? Same reactant, different products. This is why I'm emphasizing on it, because you get reactions in the exam. Same reactant, different product. Same water, but cold water, hydroxide. Same water, but as steam, oxide. Lead, copper, silver, and gold do not react with either water and steam, no matter what. Potassium and sodium, again, very reactive. They react violently with acid. Then calcium, magnesium, aluminium, as we go down the group, the reaction becomes slower. And then copper, silver, gold do not react at all. Okay, now you guys need to know the steps for the extraction of iron. These are reactions that I highly advise that you guys go ahead and learn them. Okay, what is going to happen, just to quickly summarize, we are going to add iron ore. Iron ore is hematite. We will add some coke and we will add some limestone. Okay, what is going to happen, that in the process, carbon will react with oxygen to give you carbon dioxide. This is the combustion reaction. The reason I'm going over this is because you guys will see questions where they'll give you the equation and they'll say, what type of a reaction is this? This is a combustion reaction. Okay. Then our carbon dioxide reacts with carbon to give you carbon monoxide. Okay. This is a redox reaction. Then this carbon monoxide reacts with iron oxide. And can you see that in the process, it has reduced iron. Iron has gone from being iron oxide to just iron. Iron lost oxygen. So it's reducing your iron oxide. This is a reduction reaction, right? So these are the types of reactions that you are going to see. Once the iron has been formed, it will collect at the bottom and we can remove it. Now, another really important thing is the methods of rust prevention. Again, something you guys, I'm just letting you go know the really important points that you guys need to go ahead and study. Two major methods are galvanizing and sacrificial protection. Now, the reason I wanted to go over it with you guys is because they're quite similar to each other. So what's the difference? First of all, what is it? What I'm doing is that, let's say that I have a piece of iron, okay? And I want to prevent it from rusting. If I want to prevent my piece of iron from rusting, what am I going to do? I'm going to go ahead and react it with some I'm going to go ahead and cover it with a more reactive metal. So let's say our more reactive metal is zinc. Zinc is more reactive than iron. What is going to happen? That since zinc is more reactive than iron, so zinc will react with the oxygen and it will make zinc oxide. Iron will be spared. Iron will be saved because zinc has reacted with the oxygen to give you your zinc oxide. So your iron has been spared. Your iron has been saved, right? This is what the process is. Now, what is the difference between the two of them? In galvanizing, you're simply going to coat. You make a coating. So if I take a piece of iron and I coat it in a whole layer of zinc, that's galvanizing. And if I take a piece of iron and I take a piece of zinc and I just put them next to each other, that's sacrificial protection. Okay. So in sacrificial protection, I just take two pieces of metal and I put them together. In galvanizing, you make a whole layer. You coat the entire metal in the layer of zinc. Okay. Now, let's go ahead and does anybody have any questions about what we've talked about so far? Is there anything that anybody would like to ask? We're going to go ahead and take a look at a few questions, by the way. But until then, is there anything that anybody wants to ask? Any questions? Anything that's not making sense? You guys can go ahead, ask in the chat if you guys want to. Yes, the recording is going to be shared. All right. Other than this, everything is all clear. Does anybody want to ask anything? Okay. All right. Okay. So now another important thing that we're going to go ahead and take a look at is our electrolysis. We're not going to cover the entire topic of electrolysis. We do not have the time. You guys know it's a very important topic. So we're going to be going over two portions of electrolysis. The extraction. Okay, sure. We can go ahead and we can have a 10-minute break. Sure, that's actually no problem. It's actually a pretty good idea. Thank you for suggesting it. So yes, okay, guys, we'll go ahead. We will, in fact, we'll take a 15-minute break in the middle. Okay, go ahead. So in electrolysis, there are two major things I have basically included, and that is that we have to go over our extraction of aluminium and electrolysis of sodium chloride, concentrated sodium chloride. So when we talk about electrolysis, what is electrolysis? Electrolysis is when you are breaking down any ionic compound, right? By passing electricity through it. So if I'm breaking down an ionic compound by passing electricity through it, I am doing electrolysis. Now, for electrolysis, we obviously have a condition. That ionic compound either has to be in the form of a solution or it has to be molten, right? Why? Because we need free charged particles to allow the conduction of electricity. If I want electrical current to pass through, I need those charged particles, those positive and negative ions to be free. If they are free, only then am I going to see the passage of electrical current. Otherwise, electrical current is not going to be able to pass through. So we need the ionic compound to either be, to basically be in a either molten, you need to melt it down, or you need to make a solution out. Now, along with that, we obviously have two electrodes. Those electrodes are made up of generally graphite, sometimes platinum as well, because we do not want them to react with any of the products. The positive electrode is known as anode, and the negative electrode is known as cathode. Now, this is not fixed, by the way. In electrolysis, positive is anode and negative is cathode. If you talk about a battery, a cell, because a battery also has electrodes in it. But in a battery, I am not going to use electricity. I'm going to be producing electricity, right? So in a battery, I'm producing electricity. But in electrolysis, I am using electricity. So in a battery, same concept. But in a battery, it's actually opposite. Positive is cathode and negative is anode. Okay. So please keep in mind that this thing, that positive is anode and negative is cathode, this only applies to electrolysis. Later on, when you guys especially do your A levels, you guys will study electrochemistry in more detail. So I hope you guys will remember this little concept that positive is not always anode. This only applies to electrolysis. So the positive is anode and the negative is cathode. Now, when we talk about electrolysis, let's take a simple example of molten lead bromide, right? What is going to happen that obviously we have
lead bromide. That lead bromide is going to have lead ions as well as bromide ions, right? Now, what is going to happen is this, that your lead ions are positive, which means that they will be attracted to the negative electrode. Bromide ions are negative, which means that they will be attracted to the positive electrode. Now, one thing that if you guys remember, it's going to make it much easier for you guys to solve any questions on this topic. The cathode, at the cathode, we always have reduction. Remember that. At the cathode, I will always gain electrons. At the cathode, I'm always going to have reduction. While at the anode, you always have oxidation. And this is fixed by, this is fixed. Whether you have a battery, whether you have a electrolysis, doesn't matter. This point is fixed. Cathode is always reduction, anode is always oxidation. It's not necessary that cathode is always negative. In a cell, in a battery, cathode can be positive. But there will always be reduction at cathode and always oxidation at, again, this is something you guys study in your A levels in a lot more detail. So you guys will understand it much better when you do it over there. I teach this in A levels. So you'll understand it much better then. Now, what's going to happen, that lead is going to be attracted towards the cathode. On the cathode, what do we have? We have reduction. So the cathode is going to gain electrons and going to turn into lead metal. And that lead metal is going to be deposited on the electrode. Bromide is going to go to the anode. And as it is going to go to the anode, it's going to lose electrons. Okay. Now, another tidbit. If you have trouble making these half equations, you can write it down like this. Bromide will lose electrons and it will give you bromine gas. Now, this equation I have written down is correct. Technically, it's correct. But in the exams, it's not very nice to write down electrons with a negative sign. There's no reason for it. It's just generally preferred. Examiners like to write the electrons down with positive sign. So what you do is that you shift the electrons to the other side of the equation. So your equation becomes 2 bromide ions give us bromine plus 2 electrons. Right? So this is what we see with electrolysis of bromide. And the same concepts apply when we talk about extraction of aluminium. Because aluminium is aluminium oxide. Aluminium is not available that easily. It's available as a compound, aluminium oxide. Okay? And this aluminium oxide compound is what we call, the name of the ore is bauxite. It's available as an ore with bauxite, which is known as bauxite. And it's part of a compound. It's part of an ionic compound. I need to break down the ionic bonding if I want to separate aluminium from it. So what am I going to do? We are going to go ahead and first of all, melt down our aluminium oxide. But there's a small problem. You know what the problem is? The melting temperature of aluminium oxide is quite high. It's like 2000 degrees something. 2000 degrees. So high. This is an industrial process. People are doing this in industries. They're trying to save money wherever they can. Let's be honest, right? So aluminium oxide is like, they're like, oh my God, getting the temperature to 2000 degrees centigrade. Can you imagine the amount of coal? Can you imagine the amount of heat energy you have to produce? So they wanted to come up with a way of lowering down the working temperature. For that, they use cryolite. Cryolite is a mineral. The cryolite helps bring down the melting point. So aluminium oxide is going to melt at a lower temperature. And then what is going to happen? They will place it inside your tank. These are your anodes. These are all your anodes. And
Your cathode is present over here. Your cathode is lining the tank. What is going to happen? What's going to happen is this. Aluminium oxide is going to have aluminium ions as well as oxide ions, right? Now, what is going to happen that aluminium ions are positive, so they will be attracted to the negative electrode. Oxide ions are positive, so they will be attracted to the, sorry, they're negative, they'll be attracted to the positive electrode. What is your reaction going to look like? What happens at the negative electrode? Reduction. That's all I want you guys to remember. So reduction means that aluminium is going to gain electrons and become aluminium metal. On the other hand, when we talk about our oxygen, right, the oxide ions are going to lose electrons and become oxygen gas. But like I said, we don't like to write down electrons with the negative sign, right? So we will go ahead and we will move it to the other side of our equation, just like we do in mathematics. So our equation becomes 2 oxide ion give us oxygen plus 2 electrons, right? So what are we going to observe? At the negative electrode, at the cathode, all the aluminium metal is just going to collect, which we can easily remove. The oxygen gas is going to start to be produced at the anodes. And as the oxygen gas is going to be produced at the anodes. Now, one important thing that you guys need to know is this. The anodes, especially in extraction of aluminium, this is something that is specific to aluminium. These anodes need to be replaced often. We need to keep on replacing them. Why? Because the anodes are made up of graphite. Graphite is carbon, right? The carbon reacts with oxygen to give you carbon dioxide and carbon monoxide. So what happens that since the graphite, since the anode is reacting with the oxygen, it starts to, slowly finish up. It starts to wear off. So we have to replace them frequently. But this is how extraction of aluminium is done. Now, one question that I want you guys to think about. Why am I using electrolysis to extract aluminium? But when I wanted to extract iron, I could do it with the help of carbon. There's a reason for that. And the reason for that is our reactivity series. Those metals that are more reactive than the carbon comes somewhere over here in the reactivity series. Okay? Those metals that are more reactive than carbon, I cannot extract them with the help of carbon because they're more reactive than carbon. I cannot extract them by using carbon. Instead, I need to go for electrolysis. Even though electrolysis is an expensive method, I need a huge amount of electricity to do electrolysis. It's super costly. But I have no option. Why? Because these metals are more reactive than carbon. So if I want to extract any of these metals, I will have to go for electrolysis. Those metals that lie below carbon in the reactivity series, we can extract them with the help of carbon. That's what we do with iron. We extract iron with the help of our carbon, right? So that is exactly what we go ahead and we do. So this is a cheaper method. Believe me, it's a cheaper method. It's a much cost-effective method. But when it comes to aluminium, it's just too reactive. We have no other option than to go for the extremely costly option of electrolysis. Now, when it comes to this was, I would say this is the easy part of electrolysis. You know why? Because you guys are taking a look at molten solutions. In molten solutions, we only have two ions, positive and negative. Lead, bromine, aluminium oxide. But what happens when you get to an aqueous solution? Now what? What if you have, for example, sulfuric acid, H2SO4? Now what? In an aqueous solution, you have to worry about 4 ions. What 4 ions? I'll tell you. In sulfuric acid, for example, I will have hydrogen ions from the acid and sulfate ions from the acid.
Then this is aqueous. It's mixed with water. The water is also going to give me hydrogen ions and hydroxide ions. Now it's not that easy anymore, right? Because I've got two positive ions, two negative ions. What do I do now? Okay, positive ions, still somewhat easy. Both of them are hydrogen. So obviously, who is going to go to the cathode? Hydrogen. Hydrogen is going to go to the cathode and it's going to be reduced and it's going to give you hydrogen gas. But at the anode, now I have two options. I have sulfate ions and I have hydroxide ions. Now what? So in this case, we will take a look at the reactivity series. The less reactive a metal is, the more likely it is to go to the cathode or the anode, the less reactive, meaning that if it's bottom of the reactivity series, right? If it's at the bottom of the reactivity series, the easier it is for it to go to the anode or the cathode. For example, if I have, let's say, sodium and hydrogen, who is going to go to the cathode? Hydrogen, because hydrogen is less reactive. If I have zinc and hydrogen, who is going to go to the cathode? Hydrogen. If I have silver and hydrogen, who is going to go to the cathode? Silver. The one that's low is the one that we will choose. So between sulfate and hydroxide, who is low? Hydroxide is lower. So we will choose hydroxide. Okay. So what is going to happen? That the hydroxide ions will go to the cathode. Now, this is still somewhat easy. This is the one that you guys actually see in your exams when you are doing electrolysis of concentrated sodium chloride. Okay? When you are doing electrolysis of concentrated sodium chloride, we have 4 ions. NaCl has 2 ions, sodium and chlorine. One second. Just 1 second, guys. Right. So what is going to happen that over here, we will have our hydrogen. We are going to have our sodium, right? Sodium chloride is going to have NaCl. And water is going to give me hydrogen and hydroxide. Now, between sodium and hydrogen, which one is going to go to the cathode? You go back to your table. You will see who is lower in the table. So between sodium and hydrogen, hydrogen is lower in the table. So hydrogen is going to go to the cathode and hydrogen gas is going to be produced at the cathode. Now, what is going to happen when we talk about when we go ahead and we talk about our chlorine? What happens at the anode? We have two options, hydroxide and chloride. If we take a look at this table, you can clearly see that hydroxide is lower. So I just told you guys that you will pick the option that is lower, right? Not in this case. This is exactly why I put it here. Not in this case. You'll pick chlorine. Why? Why are we picking chlorine? Miss, you just said that we picked the lower one. That the lower one is the one that's going to go. Why? Then why are you saying chlorine? The reason I'm saying chlorine is because this is
concentrated sodium chloride. If it was dilute, that would be a different solution. This is concentrated sodium chloride. Even though chlorine is higher in the series, but because it is concentrated, it is so much concentrated, the concentration of chloride ions is so much that it overpowers the hydroxide ion. So who should go to the anode? Hydroxide. But who does? Who ends up going to the anode? Chloride. Why? Because chloride is much, 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 much more concentrated. So chloride ions will go to the anode and chlorine gas is going to be produced. Now you can ask me, Miss, if the reason is concentration, then this is concentrated sodium chloride. So sodium is also concentrated, Miss. If chlorine is concentrated, so is sodium. So between sodium and hydrogen, then why are you picking hydrogen? The reason is because the difference between sodium and hydrogen is too much. The difference between sodium and hydrogen is too much. The concentration of sodium, yes, you would be right if you said it. Sodium is going to be very high in concentration. But the concentration of sodium is not high enough to overcome the difference. The difference in reactivity is just too much. In between chloride and hydroxide, the difference is not that much. So when the concentration of chloride ion increases, chloride ions are the ones that's going to go to the anode, not hydroxide. But between sodium and hydrogen, the high concentration of sodium is just not strong enough to overcome the difference. So hydrogen is going to go to the cathode. Now, hydrogen is going to go to the cathode. So what will you see at the cathode? Hydrogen gas. Chlorine is going to go through the anode. So what are you going to see? Chlorine gas. And what are you going to be left behind at the end of it? You will be left behind at the end of it with sodium and hydroxide. That's what you're going to left behind with, sodium and hydroxide. Hydrogen ions have gone to the cathode. Fluorine ions have gone to the anode. You'll be left with sodium and hydroxide ions. So you'll be left with an alkaline solution, that is sodium hydroxide. And that's very interesting. Why is that very interesting? Because this process, the electrolysis of concentrated sodium chloride, is done on a wide industrial scale. It gives the people hydrogen gas, which has got a lot of uses, chlorine gas, which has got a lot of uses. You use chlorine for making bleach in your pools as a disinfectant, and it gives sodium hydroxide, which is again a chemical that's used quite a lot in your chemistry. Now, like I said, electrolysis is just one part of the topic, right? If we talk about a cell, a battery, so a battery works on the principle of electrolysis, only I am not going to be providing energy, I am going to be producing energy. I'm going to be making energy. Okay? So in this process, this is one of the batteries that is used, that is pretty good, that you guys need to know about. And that's hydrogen oxygen fuel cell. The process is quite simple. I will take my hydrogen gas and add it to my battery. And I will take my oxygen gas and add it to my battery. Now, what is going to happen in the process? Hydrogen is going to be oxidized. Okay. Hydrogen is going to be oxidized to give you hydrogen ions and electrons. Oxygen is going to be reduced. Okay. Oxygen is going to be reduced and it is basically going to react with your hydrogen ions to give you water. Okay. So what is actually happening? I am putting in hydrogen and I'm putting in oxygen. Hydrogen is going to be oxidized. Oxygen is going to be reduced. And the final product is going to be water. This is why this is a very good option for fuel these days. Because we are producing water as a byproduct. No
chemicals, no toxic gases, no carbon dioxide, no nitrogen oxide. We are making water. It's a very, very, very good way of actually producing energy, right? So that is how your hydrogen oxygen fuel cell is going to be working. And in the process, what is going to happen? You can see that we are producing electrons, right? Those electrons are going to travel from one electrode to another, right? Because one electrode, we add hydrogen. The other electrode, I add oxygen. So hydrogen will release electrons. Those electrons will go to oxygen and oxygen will gain electrons. So electrons will travel from one side to another. And we do have a physics class coming up tomorrow, in fact. The flow of electrons gives us current. So electrical current is generated. That is how your hydrogen oxygen fuel cell works. So that is what you guys need to know in the topic of electrolysis. Make sure you guys know extraction of aluminium. Make sure you guys know. I'm not sure, you can ask, but I believe business is on Sunday. So we are going to, you guys should know about your aluminium. You guys should know about exactly how the electrolysis of concentrated sodium chloride happens and why is it that we get chlorine at the anode instead of hydroxide ions. Also, you guys should know how to make your half equations. Now, the last thing that we are going to take a look at today, before we do our past papers, is we're going to just overview our mole calculations. So, talking about our mole calculations, there are three formulas that I'm going to tell you guys right now. And then we're going to take a look at practice questions on it. Okay? The three formulas that I have for you guys is one. This is a formula that you guys are going to be using for solids, mostly solids, not always. Do not take this as like a fixed rule, but if you are dealing with a solid, you can use the formula moles is equal to mass over mr. What is mr? mr is the molecular mass, right? Do not worry, we will be going over calculations on this. So our solid, if you want to find out the moles of a solid, again, not rule of thumb, but this is the rule you can use most of the times. Solid moles is equals to mass divided by whatever the mr of the compound is. Then, if you find yourself dealing with a liquid, one second. So for liquids, we are going to do concentration is equals to moles upon volume, right? So for liquid, we use this formula. Concentration is equals to moles upon volume. And finally, if you're dealing with a gas, so for a gas, you can use the formula volume divided by 24 dm cube. This is equal to the number of moles. So if you want to find the number of moles of a gas, simply take the volume of the gas and divide it by 24. Just something to add, extra information. Where do we get the number 24 from? Well, I'll tell you guys. The 24 dm cube is the volume a gas occupies, 1 mole of a gas occupies at room temperature and pressure. So that is normal room temperature. The volume occupied by 1 mole of gas. So 1 mole of gas will have this much this much volume at room temperature and pressure. 1 mole of gas will have 24 dm cube of volume at room temperature and pressure, right? 3 formulas. I'm making this as simple as I can. 3 formulas. And now
let's go ahead and take a look at some calculations. Give me a second. Let me share the question with you. We're going to take a look at calculations. We're going to see exactly how you guys are going to solve your past paper questions. I'll tell you guys some tips, some tricks of exactly how you're going to go about solving your questions. So give me just 1 minute. Right. Now, go ahead and let's solve this together. We're all going to solve this together. Okay. Now, the equation for the reaction is given to us. We have some zinc. It's reacting with sulfuric acid to give us zinc sulfate and hydrogen gas. By the way, we just studied a similar reaction in the topic of acids and bases, where I told you guys that we take our metal, we react it with acid, we get salt and hydrogen gas, right? See, the same, all the topics just happen to be linked to each other. Okay, so what are they saying? They're saying that 25 centimeter cube of 2 mole per dm cube sulfuric acid is added to excess zinc. What do we have? Let's list our information. Remember, you guys want to solve questions, especially numerical questions, not just for chemistry, but also for physics. Remember this, even mathematics. Always try to make a small data. Write down all the data you have. It'll make questions much easier for you. So we have concentration of HCl, which is given to me as 25 centimeter cube. You guys are automatically going to note down what? You guys are going to be noting down what units are provided to you in case conversions are needed. Also, highlight your questions as you go along. Then we have the concentration of HCl. Then we have the concentration of HCl as well as the volume of HCl, right? We're going to write this down. Keeping special emphasis on units. Please do not forget, units are really, really, really important. Always keep an eye out. Thank you, Vadiha. It's H2SO4. You're right. Thank you so much. So you always keep an eye out on your units, exactly what the units are. Okay. Now, after that, what are we going to go ahead and do? Let's continue what the question is saying. They're saying excess zinc. This is important. Why is this important? Remember this, that whenever you're doing mole calculations, so oftentimes we have to do mole ratio, right? We do not use the reactant that is in excess. The reactant that's in excess is not used in mole ratios, okay? Because that is in excess. We have more than we require. Always use the limiting reagent, the one that is in less quantity for your calculations, right? So we do not need to worry about zinc. Why do we not need to worry about zinc? It's in excess. Then they're saying calculate the volume of hydrogen formed at room temperature and pressure. Okay, let's go ahead. They're saying calculate the number of moles of sulfuric acid. First thing you guys are going to do, oh, sulfuric acid is a liquid. What was the formula that my teacher taught me? Yes, concentration is equals to moles over volume. So this is the formula you're going to use. The concentration provided to you is 2 mole per dm cube. We do not know what are the moles of the acid. The volume given to you is 25. Now, my major tip to you, number one, guys, please pay attention to the unit given, right? This is in centimeter cube. Your concentration is in dm cube. If you apply, do the calculations as it is, you guys will get an incorrect answer. You guys have to remember to do conversion. So you will have to convert the volume into dm cube. My tip number one, always, 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 always take a look at units. That's where they're going to trick you most of the time. So I need to convert my centimeter cube into dm cube. How do we convert centimeter cube into dm cube? Divided by 1,000. So I will solve for the number of moles. My number of moles are going to be 2 multiplied by 25 divided by 1,000. Right? If we go ahead and we calculate, would somebody like to let me know what the answer is?
0.05.
0.05 is absolutely correct. So the value that we have over here is 0.05. Okay. Now that we have the moles of HCl, sorry, sulfuric acid, we now need to figure out the moles of hydrogen. We are now going to use our mole ratio. Okay. So this is exactly why I said we do not use the excess reagent. So zinc is in excess. If in the exam they had given you moles of zinc and sulfuric acid, if in the exam they had given you both, and then they said, okay, can you please go ahead and now tell us what is the value for hydrogen? You will not use zinc for your calculations. Why? Zinc is an excess, right? Zinc is an excess. So we always use the one that's not an excess. So sulfuric acid, hence we'll be using. Yes, you're perfectly right, by the way. The mole ratio over here is 1:1. It's an easy question. Mole ratio is 1:1. 1 mole of sulfuric acid is reacting with 1 mole of hydrogen. So the moles of hydrogen are also 0.05. Finally, they're saying now find the volume of hydrogen. What are you guys going to do? Hydrogen is a gas. My teacher told me that if you want to find the moles of a gas, do volume divided by 24. Exactly. So the moles are 0.05. We don't know what the volume is. Divided by 24. Would anybody like to do the calculations? Let me know what answer you guys are getting. Sorry?
1.2.
1.2. Yes, that is correct. Good job. That is absolutely correct. Right? 1.2. So we are going to do 0.05 multiplied by 24. 24 will come in the numerator. 0.05 multiplied by 24 will give you 1.2. Okay, Raneem, can you tell me which part? Like, do you want me to go over the entire question, or is there a specific part of
No,
it
just
that you
the
did not get?
hydrogen
Just
part.
the last part? Okay, all right. So the moles of hydrogen that we have are 0.05, right? The moles of sulfuric acid are 0.05. Okay. Now, the sulfuric acid is 1. There is 1 of sulfuric acid. And there is also 1 of hydrogen gas, right? So, since sulfuric acid and hydrogen gas are both equal to each other, both of their ratios are 1:1. I will go over another question with you guys where the ratios are different. Because the ratio is 1:1. For 1 sulfuric acid, we have 1 hydrogen. So, whatever are the moles of sulfuric acid, the moles of hydrogen will be the same. Right? Now, when we talk about yes. So when we talk about our moles of hydrogen are 0.05. Hydrogen is a gas. The formula we use for gas is moles is equal to volume of a gas divided by 24 dm cube. The moles of a gas are 0.05, right? We just got them over here. We don't know what is the volume of hydrogen gas. That's the question given to me. 24. So volume divided by 24 is equal to 0.05. Cross multiply, right? So volume is equals to 24 multiplied by 0.05. So volume is equals to 1.2 dm cube, right? Making sense now? Clear now? Anybody has any confusion? Is it making sense now?
Miss, can you just explain the part when you deduce the number of moles?
Right. Okay. So when you're talking about the number of moles, right? Now, okay, in fact, give me 1 second. Let me open up a question in which the mole ratio is slightly different and it'll make more sense. Give me 1 second. Hold on. I will explain this 1 second.
Miss, what was the answer for the RTP? The last question?
1.2 DMQ. I will tell you exactly how we're deducing the mole ratio. 1 second. Okay. This is, I think, will be easier. Okay. So let's again, quite similar questions. You guys will notice that these mole questions that have been coming in recent papers are quite similar to each other. So do practice them as much as you can. Okay.
First of all, as we go along, we highlight the important information. The equation for decomposition of aqueous hydrogen peroxide is shown to you. 50 centimeter cube of 0.2 mole dm cube solution of hydrogen peroxide is used. So I want you guys to make data sheet as you go along. The concentration is 0.2 mole per dm cube. The volume is 50 centimeter cube. And note the unit. I always want you guys to be keeping your eyes peeled for what the unit is. First is first, calculate the number of moles of hydrogen peroxide. Okay, can somebody tell me what formula will I be applying over here? What do you guys think? Hydrogen peroxide is a liquid, right? Yes, correct. So concentration is equals to moles over volume. Your concentration is 0.2. We don't know what are the moles. The volume is 50 centimeter cube. Do remember to do conversions, otherwise your answer will be incorrect. So I will take my 50 upon 1000 into the numerator. So this will become 0.2 multiplied by 50 upon 1000. This will be equal to the number of moles. So will you guys please calculate for me? What should I get as my answer?
0.01.
Correct. Now, you can see that I have the number of moles of hydrogen peroxide. So this is what you were asking me. How do we deduce the moles of the oxygen? So we have to find out the moles of oxygen. Now, this is how you guys are going to do it. Look, what are the moles of hydrogen peroxide? 0.0. What is the mole ratio? So when I say mole ratio, look at the balancing. What is the, because when you balance the equations, you write down you balance the equation, you write down the number of molecules, right? So over here, we have 2 molecules of hydrogen peroxide, or 2 is the ratio of it. So for 2 hydrogen peroxide, we only have 1 oxygen, right? Can you see that? We don't have anything written next to oxygen, right? That means 1. So for 2 hydrogen peroxide, we have 1 oxygen. So this is what you guys are going to do. The moles of hydrogen peroxide are 0.01. What is the mole ratio? So mole ratio will be the number written next to it. So we have 2 of hydrogen peroxide. Okay. Now, what are the moles of oxygen? We are not aware. So we write down X. What is the mole ratio? What is the number written next to it? There's nothing written next to it. So that means 1. Right? And then you solve for X. So you will basically end up doing 0.01 divided by 2. Right? Because 0.01 multiplied by 1 is 1. So you get 0.005. This is how you are deducing the number of moles. In the question that you and I just
we just considered this question, the previous question, this one. Okay. In this question, see, there was 1 of sulfuric acid and 1 of hydrogen. Okay. So let's say if the moles of our sulfuric acid were coming around 0.05, right? So 0.05, these are the moles of sulfuric acid. Then we have 1 of, the mole ratio is 1, okay? We don't know the moles of hydrogen. So 0.05 is equals to X. That's how we figured it out, okay? So this was a simple, for 1 sulfuric acid, 1 hydrogen. In this particular question, if you come over here, so in this particular question, we have a 2:1 ratio. So if the concentration is 0.01, so 2 of hydrogen peroxide is 0.01. So X of oxygen, you can solve, right? Making sense now? Do you understand how we're reducing the value?
Understood the deducing value. Just want to like understand how why is it equals to x over 1?
Okay, because if you take a look, see for how, what is the number next to oxygen? There is no number written next to oxygen, right? So that means when there's no number written next to it, it's an automatic 1. That's what, if there's only 1 molecule of oxygen, what this basically means is that 2 molecules of hydrogen peroxide will react to give you 2 molecules of water and 1 molecule of oxygen. So it's basically telling me how much of the product is going to be made. Okay. So if there is nothing written next to the in the equation, if there's nothing written next to the product or the reactant, it automatically means that there is 1 of it. Okay. So I have 2 of hydrogen peroxide. So 0.01 is the value for 2 hydrogen peroxide. So what will be the value for only 1 oxygen? Right? That's the reason why I'm writing 1, because this is basically telling me the numbering. So I have 2 of hydrogen peroxide, but only 1 of oxygen. So if 0.01 is for 2, then how much will be for 1, right? And that's how you get the value of X. If you want, like, right? Making sense? Do you understand why we're writing down 1? If there's nothing, for example, there's nothing written next to the oxygen, right? That automatically means that there's only 1 oxygen. That's it. It means there's just 1 oxygen. It's guaranteed, like it's always there. Okay. If you have more than 1 oxygen, it will be mentioned next to it. 2, 3, 4, 5 in balancing of the equation. Okay. So this is basically what I'm doing. That 0.01 is the value I got for 2 hydrogen peroxide. But I don't have 2 oxygen. I only have 1 oxygen. This value is for 2 hydrogen peroxide. So how do I get the value for 1? This is the value for 2 molecules. How do I get the value for 1 molecule? So that's what I'm doing. 0.01 is the value for 2. So what would be the value for 1? Right? Is this becoming clearer now? Do you want me to go over it again? Is there any confusion? Anything that anybody wants to ask? Okay. Once you have found the number of moles of oxygen, right, we have to find the mass of oxygen. So this is a gas, but they're asking you to find the mass. That's why I said that the rules are not hard and fast, right? We can use the formulas. I told you a formula which was moles is equals to mass over mR. I told you this is for solids. But I said that's not a hard and fast rule. I can also use it for oxygen. So if they ask me to find the mass, I will use moles is equals to mass over mR. The moles that we got were 0.005, right? Now, we don't know what the mass is. That's what they're asking us to find. What about the mR of the compound? How do we find the mR? You will open up your periodic table. When you open up your periodic table, you guys are going to take a look at the mass number. Okay. So you guys are going to go ahead and you're going to take a look at your mass number. The mass number for oxygen, I remember them, so I'll just tell you. The mass number for oxygen is 16. Okay? You'll take a look at mass number. So the mass number for oxygen is going to be is 16. So you'll take the mass number, this number 16. You'll take the mass number and you are going to use that for calculating your MR. How do we do that? We are going to, in the formula of oxygen, we have 2 atoms of oxygen. Okay? So one oxygen will have the mass of 16 and the other one will also have the mass of 16. So we will do 16 multiplied by 2 because there are 2 oxygen atoms. And 16 multiplied by 2 gives us 32. We will take this in the numerator. 0.005 multiplied by 16 into 2. And this will give us the mass. So when we calculate the mass, what do we get as our mass? We get, can somebody calculate for me? Yes, 0.16. Yes, correct. Good job. 0.16. Okay, that is going to be our answer. Let's take a look at another question. One second. And the more you guys practice these more questions, by the way, the easier the entire topic is going to get. Once you get the hang of them, it's much easier to understand. Okay, this is a question. Yeah, Madiha, you'll get access to the PowerPoint. Okay, this is our last question basically for today as well. This is a question that involves mole calculations and it involves finding the value of water of crystallization, right? So if you take a look, you will see that we have, look, this is the nickel sulfate salt, but it has water molecules attached to it. So this is a crystal. It's a crystal, right? What is this? This is water of molecule. This is water of crystallization, right? In an experiment, again, we are going to be highlighting as we are going along, right? In an experiment, 0.454 grams of nickel sulfate crystal is used. The mass of anhydrous nickel sulfate remaining is 0.310. What are they saying? What they've done is basically they have taken nickel sulfate crystal. That crystal has a mass of 0.454. Then what they did was they decided to heat it up. Now, do you guys remember what I said about heating up crystals? What happens if you evaporate all the water away? If you evaporate all the water away, all of the water of crystallization is lost and you're left with like a white powder, right? That's what happens. All of the water crystallization is lost and you are left with a white powder. That's exactly what they did over here. They took a crystal with the warm water molecules included. They heated it up. And as they heated it up, the mass decreased from 0.454 to 0.310. Why did the mass decrease? Because all of the water of crystallization was lost in the form of water vapors. And that's why, see, it went from being hydrated to anhydrous. Anhydrous means without water. Now, They are saying that you basically have to find the value of X. What is X? X is the water of crystallization. We have water molecules in the crystal. But how many? We don't know. That's what we want to find out. How many crystal water molecules are there exactly in one crystal of nickel sulfate? So they're saying, please find that out for us using the following steps. They give us steps which makes things, to be very honest, not that hard. First of all, they're saying calculate the number of moles of nickel sulfate remaining. Again, please pay attention to exactly what they're asking. So we have to use remaining, meaning that what we have towards the end of it. We have to use the remaining. Okay? So let's go ahead and calculate then. Fine, we will calculate for remaining. Now, first of all, who can tell me what formula should I be using? Please take a look at the data that we have. We have been given with the MR of the compound and we have been given mass of the compound. Yes, correct. We are going to use moles is equals to mass over MR. They are saying remaining. If they're saying remaining, number of moles of nickel sulfate remaining. So what mass should I take? They have given me two masses. Which mass should I take? If they're asking me to calculate the number of nickel sulfate remaining. Yes, correct. So you are going to take 0.310. Divide that by the MR. They were nice enough to give it to us. So we will take the value provided and calculate the number of moles. Can somebody let me know what are the number of moles that we get? Correct. 0.002. Perfect. Now, the next part they're saying, calculate the mass of water given off. How can we find the mass of water? Again, much easier. This question, this part, much easier than it seems. No complicated formulas needed. No complicated formula needed. None. Very simple thing. Nope, no ratio, nothing. I'll give you guys a hint. The initial mass was 0.454. After you evaporated all of the water, you were left with 0.310. The mass decreased. How did the mass decrease? Why did the mass decrease? Yes, you're correct, Madiha. We're going to subtract them. We're going to subtract the two masses. This was the mass with the water. This is the mass without the water, right? Mass, this is mass. This is nickel plus water. And this is just nickel on its own. All the water is gone. So if I subtract the two values, I should be able to find out exactly what the mass is, right? I'll take the mass. This is exactly how I'm going to find out. That's why I said no formula needed. Very simple calculation. We know the mass of nickel plus water. We know the mass of nickel on its own, right? That's why we had nickel sulfate remaining because all of the water evaporated away. So we're simply going to go ahead and subtract the two values and we're going to get 0.144. So the mass of water is 0.144. This is exactly why I said read the question carefully, right? Everything is in the question. Read it carefully. No complicated calculations needed. We know the mass of nickel with water. We know the mass of nickel without water. So we simply subtract the two and we should be able to find out the mass of water, right? Now, let's see what they are asking us next. They are continuing the question and they are basically saying that calculate the number of moles of water given off. So now we have to calculate the number of moles of water. Okay. Now, how are we going to find out the moles of water? Now, this is where you guys are going to have to use some mole calculations. Yeah. So what? Now go ahead. Tell me, what formula would I be applying over here? I need to find the moles of water. What information do I have? I have the mass of water. Yes, exactly. We are going to do
Moles is equals to mass over mr, right? So when we're going to go ahead and we're going to talk about it, what are we going to do? We are going to, mass given to me is 0.144. The mr is 18. So can somebody calculate the moles and let me know?
2.592.
0.144 divided by 18.
You have to divide it, 0.144 and divide it by 18. Yes, yes, Fatina, it's going to be 0.008. Okay, 0.008. So now we have the moles of water. Let's see what they ask us next. Next, they're saying, now calculate the value of X. Now, when you are solving questions on water of crystallization, let me go ahead and tell you, what do you do. So you can get to the moles of water. After you have the moles of water, you want to find out what is the value of X. In this case, what are we taking a look at? Mole ratio. We have 1 nickel sulfate. Is there any number written next to nickel sulfate? No, we have 1 nickel sulfate. But is there a number written next to H2O? Yes, X. So 1 nickel sulfate and XH2O. Yes, dear, you're correct. 1 nickel sulfate and XH2O. So we will take out the mole ratio just like I taught you, right? The moles of nickel sulfate are 0.002. Okay. So 1 nickel sulfate is 0.002. So how much water? Because we have X water. So X water, what are the moles of water? 0.008. Right? The moles of nickel are 0.002. The moles of water are 0.008. So 1 nickel sulfate is equals to 0.002. So X is going to be equal to, so X is the number of molecules of water. We don't know what is the number of molecules of water, but we know whatever the value is, it is equals to 0.008. So we are going to go ahead and calculate. So we are going to go ahead and do 0.008 divided by 0.002, and you guys are all correct. It is going to be 4. So how many water of molecules do we have? What is the, with 1 nickel sulfate, we will have 4 moles of, or 4 molecules of water. And that is how we are going to be solving these questions. Okay, guys, so we are going to go ahead and we're going to be stopping over here. I really hope that this helped you guys a lot. In fact, I hope it helped you guys a lot with your studies. I know you guys have exams coming up. Best of luck from my side, you guys. I hope, inshallah, each and every one of you do really, 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 really well. Please don't forget to check out our website. That's where the resource center is. After the class, you will be provided access to the website, right? So make sure you guys note all the information down. You have sent your information in the group. After the class, our admin team in a bit, they're going to give you access to the website, okay? Once you have access, so you will have access for about a month until June 15th as a present from our side, right? Because we know you guys are quite close to the exams. So as a present from our side to help you guys out, prepare for exams, we're going to give you access to the course. You guys are going to have access to the entire course, right? So you guys can go through all of the lectures in detail. Normally what we do is that obviously we take detailed classes, we teach, we do past papers. That's how I teach anyway. I take classes and I always follow it up with past paper practice, and we take our sweet time doing it, right? This was just a small session to try to help you guys as much as we can. You guys will be given access to the resource center as well. And we are, by the way, starting our new batches as well for the next year. AS level, May, June, we are starting our batches from August. For our October students and Gen Feb students, we are starting classes this June. So I really hope you guys enjoyed this session. You guys had some fun. I really hope it helps you out. Best of luck to each and every one of you. No, Madiha, we don't have the time actually to go over equilibrium. If I wish, that's what I'm saying. The syllabus is so long. I really wish that I had the time to sit down and just, go over everything with you guys in detail, but we do not have the time. So really hope this helped you out, you guys. And I really hope actually that you guys are going to join us as well starting next year. And I will see you guys. I'll see some familiar faces. Best of luck, everyone. Have a good day. You can contact the department for information regarding that. I don't know that information. The admin department knows. You can contact them. Anyways, best of luck, guys. Thank you so much for coming for this session. I really hope I will see you guys for your A levels as well. Best of luck, guys.
Just 2 minute,
Yeah.
Fatma, if I can just quickly add to everyone. First of all,
Yes,
best of
yes.
luck, everyone. I'm the guy who's from the admin. Uh, See, we always have limited seats. So I know many students contact us. I'm the guy who's always responding to you on WhatsApp and Instagram. And I understand that most of you guys contact us, but please make sure to join us in time if you wish to. That is August. So if you're planning to do your AS next year, join us in August so we can give you the seats because we always have limited seats. Anyway, wish you all the best and thank you so much.
Okay, thank you so much, Abdullah. Thank you so much, everyone. Best of luck for exams. Inshallah, I know you're all going to do brilliantly. And hopefully I'll see some of you next year as well. Okay.